Right. Good morning, good afternoon, everyone, depending on where you are. Thank you for joining this joint generator interconnection workshop. So we are, pretty pressed on time. So I'll pass the word to Wayne Sipperly, who is Executive Director of North American Generator Forum, to give some opening welcoming remarks. Wayne, the floor is yours.
Thank you, Julia. So the North American Generator Forum, or the NAGF, is pleased to be a sponsor for this workshop. The NAGF and ESIG have a history of collaborating to develop workshops for Ferc, NERC, and industry as a means to discuss important bulk power system issues and share information. When Mark Ahlstrom contacted us back in March of 2022, this year, to discuss this potential workshop, the NAGF was more than happy to support, as the issues to be discussed at this workshop regarding the changing generation resource mix and impacts on the generator interconnection are currently front and center. The transition to a generation resource mix dominated by inverter-based resource generation is only increasing due to state climate mandates and federal policy. Therefore, this is one of the key issues facing the electric industry right now. Workshops like this enable Ferc, NERC, and industry to demonstrate that they can come together and work to address such issues to ensure the reliability and resiliency of the bulk power system now and in the future. I would like to thank the ESIG staff and others responsible for bringing this workshop together. Identifying speakers, developing presentations, and dealing with logistical issues requires significant time and dedication that are often on top of normal work assignments. Thank you for your efforts, and I believe this workshop will be both informative and a huge success. So Julia, I'll turn it back over to you.
All right, thank you so much, Wayne, for welcoming us all. So my name is Julia Matevosyan. I'm a chief engineer at Energy Systems Integration Group. I'll provide some further opening remarks before we open up. So for those of you not familiar with ESIG, we're Energy Systems Integration Group. We're a nonprofit membership-based educational association. ESIG provides workshops, discussion forum, resources on evolving energy systems. ESIG supports engineers, researchers, technologists, policymakers, and public with energy systems transformation in a way that's economic, reliable, sustainable, thoughtful, and collaborative. We have more than 200 members globally, and here on the right-hand side, you can see the makeup of our membership. So as Wayne mentioned, this workshop is a joint one, and we joined forces with North American Generator Forum, North American Electric Reliability Corporation, and Electric Power Research Institute, and we would like to thank all our partners for supporting this workshop. So this workshop is not the first one. We had two previous ones in 2018 and 2019, focusing on energy storage and then more broadly on hybrid resources, energy storage, and provision of essential reliability services. And then this workshop today is focusing, tomorrow, and the day after tomorrow is focusing on generator interconnection. So as you probably all know, interconnection queues around the US are backlogged by more than 1,400 gigawatts of generation projects facing multi-year study delays. And in order to address those gaps and speed up interconnection process, Federal Energy Regulatory Commission recently issued a notice of proposed rulemaking on improvement of generation interconnection procedures and agreements. Additionally, in April this year, IEEE 2800 standard has been approved. This is a standard outlining minimum interconnection requirements for inverter-based resources connecting to transmission and sub-transmission levels. The standard was developed with wide industry participation, and it had extremely high approval rate during voting. There is also a growing number of disturbance events highlighting gaps in existing interconnection study practices, modeling, and interconnection requirements. And so here on the slide, you can see NERC reports on the events lining up. So all of these issues are related to generator interconnection and require immediate attention, and therefore we thought that organizing this workshop was timely and beneficial for all stakeholders and policymakers involved. Additionally, recently, the Department of Energy has kicked off Interconnection Innovation Exchange Initiative. This is DOE initiative which convenes diverse stakeholders involved in interconnection of solar, wind, and energy storage resources to facilitate peer learning, knowledge exchange, and inspire new interconnection ideas and capabilities. So we'll cover the scope and roadmap for this initiative towards the end of our workshop. So just to outline the purpose of the workshop, we'll strive to identify gaps and recommended best industry practices related to generation interconnection process, interconnection studies, modeling, and interconnection requirements and standards. We'd like to inform industry comments to Ferc NOPR, but also bring awareness to developer community about power system reliability needs, which are shaping studies, modeling, and interconnection requirements. On the other hand, we'd also like to bring awareness to independent system operators, RTOs, and utilities and policymakers on challenges facing project developers. We would like to inform broad engineering policy and decision maker audience. After the workshop is concluded, we'll summarize workshop highlights and key messages in 3 blog posts, which we'll post towards the end of September. So just to provide a short overview of the agenda of the workshop, the first day will focus on interconnection and transmission planning processes. So the first session of the day will discuss differences between generation interconnection process and transmission planning process, and why is this different and is it really needed? Then the second session dives deeper into the integrating interconnection and transmission planning processes, as well as focuses on benefits of transmission beyond production cost saving. Then jumping on to the second day, we'll talk about interconnection studies and modeling. So the first session of the day will focus on interconnection studies and reliability needs behind it, while the second session zoom into specifically modeling questions. On the third day, in the first session, we'll talk about IEEE 2800 standard and how that came along and what's the roadmap for dissemination. And then the last session of the workshop, as I mentioned, will focus on DOE I2X initiative. I'll then close with some closing remarks where I'll try to bring up key points from presenters' presentations and from each day. And then these key points we'll also use while writing the blogs, summarizing the results of this workshop. Right, so some of the workshop logistics, the phones will be muted for the duration of the workshop. Please use slido.com and event code ESIG9 for today, ESIG10 for tomorrow, and ESIG11 for the day after tomorrow as a code. So as you go on slido.com and put this code, you log into this event Q&A, and you can post your questions there. You can also vote your questions. You can also vote on already posted questions, and that helps us prioritize the questions and also avoids repetitions. Please do not use the chat window in the WebEx because we'll use Slido for Q&A. All presentation materials will be posted on the event page. This workshop is recorded, and the recording will be made available on ESIG YouTube channel shortly after the event. You'll receive confirmation email once presentation has been posted, and again, once the recording is available. Also, an email with a link will go out once we have posted the 3 blog posts that I've mentioned previously. All right, so with any further ado, thank you so much for joining and enjoy the workshop.
So starting with the first panel, my name is Warren Lasher. I'm an independent consultant down here in sunny Austin, Texas, and it is really my pleasure to be participating in this next panel. The panelists that we're going to be hearing from are Hannes Pfeifenberger with the Brattle Group, Aaron Vandervorst with Enel Green Power, and then Aurea Catanase with Electric Power Engineers. And they're going to be laying the groundwork for some of the challenges that we have with the current interconnection processes. As a reminder, I'm going to be watching the slido.com, the questions that you enter, and then at the end of the session, I will take some of those questions and I will present them to the three presenters and get their thoughts on some of your questions. So with that, I'm going to turn it over to Hannes. He's going to kick us off. There he is. Okay, thank you.
Thank you, Warren. Let's see if I can manage to share. Can you see my screen?
Yes.
Great. Well, thanks, Warren, for the introduction. Thank you to ESIG and the sponsors for inviting me. This is a very important topic. Its complexity is considerable and often underappreciated. So let me try to give you an overview of how generation interconnection and transmission planning work together. This is just an overview of how generation interconnection and transmission planning relate to each other. Each box is usually a distinct planning process. So you see there's a planning process for local reliability project, for generation interconnection projects, for long-term transmission service related upgrades, for regional reliability projects, for regional economic and public policy projects, and somewhere in there, some interregional coordination. 90% of all transmission investments, of which there are about $25 billion a year, are solely driven by reliability criteria. And an increasing part of those transmission reliability upgrades are driven by generation interconnection process. I think the idea here is that the siloed process is really not very good at finding cost-effective solutions for the long term, because all these needs and all these reliability and economic and public policy objectives are happening at the same time, and the next decade or two will be critical in making this work. A siloed project planning process with reactive reliability-driven planning results in piecemeal higher cost transmission solutions that increase the total costs faced by electricity customers. So we really need to get to a more proactive planning process that holistically and proactively considers our future needs. We already know what state clean energy goals are, and to achieve them needs a more integrated planning process, which, as I will explain, also means the generation interconnection process needs to be better integrated with proactive transmission planning. And sorry, I have problems with my slides here. Oh, there we go. The first challenge here is really that the generation interconnection process takes a long time and results in very costly transmission upgrades that are usually allocated to individual generators requesting interconnection. As you can see on the chart here, going through the interconnection study process to just get an interconnection agreement takes between 20 and 40 months. And if you look at the individual interconnection queues, many of the projects in the queues are more than 500, or many are more than 1,000 days old. So clearly we have a situation that is not conducive to achieving clean energy goals in a expedited fashion. The other thing, and we will hear more about this from Aaron in the next presentation, is that study criteria that are being applied to generation interconnection requests often trigger deep or very distant network upgrades that are also very expensive. In this one example from NL, you see a 300 megawatt project requesting energy-only non-firm interconnection in North Dakota is triggering dozens of upgrades throughout the region. Some of them are as far away as 1,000 miles down in Missouri. For a non-firm energy-only interconnection request, you really don't want to have study processes that cause these very distant upgrades. It also means that these distant upgrades, and a lot of that relates to the coordination with affected neighboring systems, it just exponentially increases the complexity of the studies that need to be undertaken and the time required to conclude the interconnection study process. Some of these upgrades are not even determined until after certain projects are well through the development process. The good news is that we have different models of interconnection processes in the country, and we might be able to learn from those differences. This chart just shows generation interconnected in 2021. It also shows that Texas, ERCOT, has interconnected vastly more generation, and certainly renewable generation is most of that, than the other ISOs. While ERCOT in 2021 added about 10% of the existing system capacity as new resources, ISO New England and New York added only 1%. PJM added about a third of ERCOT's if you adjust for size. But these eastern and western regions are also including the states with the most ambitious clean energy standards. So what this chart shows is that the regions with the most ambitious clean energy standards are interconnecting renewables at the slowest pace, while a place like Texas that doesn't even have any binding clean energy standard is interconnecting a lot more. There are many reasons for that, but I just point this out so we can learn from it. The interconnection process is really 5 different elements. And to improve the whole process requires that each of these 5 elements be improved. The one is just the process and queue management. Do you study individual interconnection requests? Do you study it in clusters or study years, or are you going to pool more resources into the study process? There's an issue of scope and handoff. Where does the generation interconnection upgrade? Where does the generation interconnection process trigger upgrades versus which transmission upgrades are handled through the regional transmission planning process? The study approach and precise criteria that are being used to, say, the power flow studies make a big difference, because they could trigger expensive distant network upgrades or not. And once you have identified overloads or violations, you need to select a solution. Which solutions are being selected makes a big difference. Today, grid enhancing technologies such as power flow control devices or dynamic line ratings are not usually allowed to be used in the generation interconnection process, but the Ferc no-bound generation interconnection is addressing that. And lastly, and importantly, cost allocation. It's very hard to get an efficient generation interconnection process working if individual interconnection requests trigger deep network upgrade that are too expensive for individual generators to pay. We recommend that we seriously consider reducing the scope of upgrades that are being allowed to be triggered by the generation interconnection process, and move to something that the UK calls connect and manage, which a decade ago replaced their invest and connect approach. To go from invest and connect to connect and manage in the UK has reduced time requirements for generation interconnections from 5 years to 1 year. It is also similar to what ERCOT is using, which has a much faster interconnection study process by virtue of how it is set up. But if you do move to a connect and manage type of generation interconnection process, you do need to combine it with more proactive transmission planning to address and manage the congestion and curtailment risks that are basically taking out of the generation interconnection process and into the transmission planning process. This requires both a near-term multi-value planning process that can quickly address those urgent needs, and a long-term process that looks out to the next decade or two to see what kind of resource interconnection needs are coming down the pike. We've talked a lot about what such a proactive multi-value transmission planning process should look like. It really needs to proactively plan for all the resources we need to meet states and the region's clean energy goals. We need to recognize that each transmission project offers can address multiple needs, meaning it offers multiple benefits. That kind of multi-value planning is critical to find cost-effective solutions. And in doing so, we need to be very clear that the future is uncertain and that in some years there could be very high cost, high stress grid conditions that need to be planned for explicitly. And scenario-based planning is a way to deal with that kind of uncertainty. And of course, the grid is not one project at a time. The grid is valuable because it works as a portfolio of grid assets that together are addressing our system needs most cost effectively. And then lastly, we can't forget about interregional. The RTO seams are not the seams of the grid. And to find cost-effective grid solutions, we need to look beyond the seams to do better on interregional planning. But just looking at the generation interconnection process proactively has huge advantage, even if you don't combine that with proactive multi-value planning. And one example is the MISO SVP joint targeted interconnection queue study, where MISO and SVP came together and combined several years worth of interconnection queues and figured out cost-effective solutions to address the joint violations. And the result is a 7-project, 1.6 billion transmission portfolio that is able to integrate 9 gigawatts of existing generation interconnection requests and make headroom for an additional 20 gigawatts of projects near the MISO and SPP seam. In addition to interconnecting generation, the study also found that it would reduce production costs in the MISO and SPP footprint by about $1 billion. And if you look at that, the generation interconnection cost of this proactively planned portfolio is about $58 per kilowatt with 100% participant funding, or if you allocate a portion that reflects the savings to the MISO and SPP footprint to loads, then those interconnection costs would only be $28 a kilowatt. If you relied on individual generation interconnection process, you would pay over $100 a kilowatt. So you see that combining the scope or expanding the scope of generation interconnection requests to do multiple years and neighboring regions offers substantial advantages. The same has been found by SPP when they studied how to interconnect 75 gigawatts of renewables, which the study found could be achieved at a cost of about $3.2 billion, not counting any lower voltage upgrades. $3.2 billion for 75 gigawatt is incredibly cost effective. In contrast, if you just look at the individual generation interconnection requests for 15 gigawatts of offshore wind, those came out to about $6.4 billion. So if you study interconnection needs for all the renewables needed in the PJM footprint, you can dramatically reduce the cost of generation interconnection. But it's even better if you pull the major network upgrades that might come out of the generation interconnection requests into long-term scenario-based planning. And that type of scenario-based planning has been around for decades. It's been developed by the oil companies to deal with long-term uncertainties. and it's a multi-step process. The good news is we have several regions who are actively using this process, such as MISO and ERCOT, also SPP. But to give you the MISO example, you start out with developing scenario futures of what the generation mix might look like in the future. There's uncertainty, but that's why you have scenarios where you can cover the uncertainties. And if you then develop a cost-effective transmission portfolio that addresses all reliability needs, but also reduces total costs faced by ratepayers, you end up with transmission investments. So you spend more money on transmission to save total electricity customer costs. And coming out of that long-term planning process, MISO has developed the first tranche of what they call least regrets transmission projects. And that portfolio costs about $10 billion to build, but has been estimated to reduce other costs by between $37 to $70 billion, while at the same time supporting interconnections of about 53 gigawatts of renewable resources. So you can see that this kind of proactive planning for all future need, including generation interconnection, offers substantial advantages and will ultimately also speed up the generation interconnection process, because if you pre-build the system that you need by the time you need to interconnect generation, you save yourself a big step. So to make it all work and to do so cost effectively and quickly, we really also need to rely more on advanced technologies. And that is really underappreciated right now, because most of the transmission planning processes sort of skip over these options, and the generation interconnection planning process today does not really consider these devices like smart wires or power flow control devices as a solution to address identified violations. There's a lot of experience out there now, including commercially applied technologies that have been implemented not just in Europe, but also in the US, and have been implemented with great success and at surprisingly low costs and quick turnaround. From a generation interconnection process, we need to look at these technologies as low-cost way to quickly address identified needs and near-term transmission planning if we go to a connect and manage approach. But in the long term, we also need to use these technologies to make the transmission investments more valuable, because if you can combine building major new transmission line with advanced technologies, you might be able to increase the transfer capability, maybe not capacity transfer, but certainly energy transfer capability by 50% or more. And that means the new lines are more cost effective and will reduce overall customer costs. So where does that leave us? I think the bottom line here is that generation interconnection and transmission planning are parallel processes today. They're closely related because they both are trying to build a grid. But unless we integrate these processes better, we won't get to the more cost-effective holistic solutions that we need to identify to be able to achieve clean energy goals cost-effectively. Doing that will also dramatically reduce the cost and time requirement to interconnect the large number of resources that we will need to get on the grid over the next decade or two. So to give you a sense of specific items that I think should be considered would be, the first one is that we ought to consider generation needs over a longer time frame. If we know we have public policy goals for 2030 and 2040, we need to factor that into the generation interconnection and transmission planning. We really want to reduce the scope of expensive deep network upgrades that are triggered by individual generation interconnection requests or study years, and move those upgrades into the more integrated planning process so that we can simultaneously consider multiple needs and find the most cost-effective solution that can address these multiple needs. And we need to use that multi-value planning to address both near-term needs like high curtailment and congestion that can be addressed quickly, as well as long-term needs to get the grid ready for where we need it to be in a decade or two, considering the uncertainties. And then, as I said, we ought to look beyond the regional theme. The SPP and MISO study is a good example of that. Advanced transmission technologies, improved study criteria, and then, of course, we need to find pragmatic ways to allocate the costs of this. Thank you. Warren, back to you.
Excellent. Thank you, Hannes. Before we move on to our next presenter, I just wanted to remind you, slido.com. If you just open that up and enter ESIG, all caps ESIG 9 as the code, it's really easy. Even a dinosaur like myself, I was able to just get right on, and I'm watching the questions come up. I will be taking those questions at the end of the panel session. So thank you again, Hannes. We're going to move on to our next presenter, Aaron Vandervorst with Enel Green Power. Aaron.
Great. Thanks, Warren. Can you confirm you can hear me and see my screen?
Yes, both.
Excellent. Thank you. Well, good afternoon. My name is Aaron Vandervorst. I work for Enel Green Power. I'll provide a brief background of my experience in order to highlight the work context within which I have formed my views of the electric industry. My first role after college was as a transmission studies engineer with Minnesota Power Cooperative. I managed the interconnection and TSRQ and studies and closely coordinated with MISO and Manitoba Hydro as affected systems. I also worked on many other planning and operations studies, including TPL, under voltage and under frequency load shedding, transmission design, and energy efficiency proposals. In 2017, I took a new job with Tradewind Energy, a small wind and solar developer. In that role, I primarily covered SPP, Associated Electric, Minnesota Power, and WEC utilities in Colorado. Following the acquisition of Tradewind by Enel Green Power, I now manage Enel's interconnection team for development projects spanning the US and Canada. During this time, I've personally worked on nearly 4 gigawatts of new wind projects, which have since connected to the grid and have contributed to several other wind, solar, and battery projects, which we expect to build in the future. I've also proposed and or studied several transmission upgrades, which are now in service. The purpose of my presentation today is to review a white paper, which I co-authored with Adam Stern from Enel's Regulatory Affairs team. I would be remiss not to give a huge thank you to Adam, who was instrumental in turning the concepts I proposed into written materials and for promoting the materials before Ferc and other groups. I'll focus on 2 core topics today. First, I will highlight the overall process and individual concepts from our white paper. Second, I will make recommendations regarding adjustments of the proposed rules in Ferc's interconnection NOPR. I will only cover the materials at a high level today. I encourage the audience to review the slides and white paper after the presentation to dive into more detail. The material in these slides has evolved from Enel's white paper to more closely align with Ferc's direction in the interconnection NOPR. Enel does still support the concept of an integrated transmission planning and interconnection process. However, these slides present process reforms within the interconnection process only, not as an integrated interconnection and transmission planning process as proposed in the white paper. I encourage individuals and companies to consider the merits of each approach, as well as the individual concepts as you review and comment on Ferc's interconnection NOPR. The proposal for competitive facility studies and EPC work was submitted in Advanced Energy Economy's ANOPR filing. I have given additional thought to that concept since that filing, which is reflected in the slides below. I will start with a very fast overview before we move to more detailed slides. The key overarching theme of this proposal is that consolidated holistic planning will optimize new transmission, facilitate competition, and reduce rates for load. The proposal is grouped into 4 main steps: an individual local impact study, a regional process entry and EPC kickoff, a regional cluster study, and finally, a study of more firm service types. The third box, the regional cluster study, could be either a new step in the interconnection process, or it could represent a new consolidated interconnection and transmission planning study. These 4 boxes will remain the same throughout the slides, with the current step highlighted in green. On this slide, I've created a simple diagram to reinforce the purpose of each stage of the study process. The green dotted ovals represent the area in which upgrades would be studied and assigned and will change for each step of the process. This first diagram represents the individual local impact study in the first step. The key characteristics of this study are as follows. First, the study is individual, so it only includes 1 new generator at a time. An individual study reduces the number of regional upgrades assigned to groups of interconnection service requests based on group criteria. These upgrades are better justified and designed through more holistic transmission planning studies. I recognize that this is counter to Ferc's NOPR proposal and have included options for reduced dependency in cluster studies in these slides as well. The second characteristic is using a high transfer distribution factor, or TDF, to identify upgrades. A high TDF or similar criteria for impacts to voltage, short circuit current, etc. ensures that the interconnection request is only assigned upgrades near the project that it significantly impacts. These mitigations would reasonably be expected to have a high degree of impact on how often the generator is able to inject power. The third characteristic of the individual local impact study is using reasonable assumptions about seasons and load profiles under which the generator would most commonly produce energy. This is commonly referred to as a fuel-based dispatch. This approach also ensures that an interconnection request is funding upgrades that are most impactful to its actual generating profile. The fourth key characteristic is flexibility. The individual study should allow optimization of project size, configuration to the grid, and upgrade requirements. As an individual study, this is much less impactful to other requests to use the system. The results of this study are proposed to be binding ERS interconnection upgrades and would reflect the requirements for basic interconnection service. All other upgrades beyond this step would have a related benefit that would exceed the cost of the upgrade, resulting in a net benefit to the generator. This gives generators a high degree of certainty early in the interconnection process and makes it reasonable for transmission providers to demand a high degree of project readiness and financial commitment to move forward. To reiterate, the key characteristics of the impact study are individual, local, flexible, reasonable, and binding. Suggested details are shown on this slide. Why is this approach beneficial? Most importantly, it reduces interdependency between projects due to group impacts and with affected systems. ERCOT gives us an example of this approach taken to the extreme. In ERCOT, no upgrades are assigned, so there is no interdependency between projects. Including both studies and EPC work, projects are able to achieve commercial operation in 3 years or less from application, less than half the time it takes some other RTOs to even produce an interconnection agreement. While we aren't advocating to eliminate upgrades completely, it is clear that reducing the number of assigned upgrades and the interdependency of projects accelerates the interconnection process. Reducing interdependency dramatically reduces workload for transmission providers, the need for restudies, and the impact of withdrawals on other interconnection requests. This leads to more efficient processing of the interconnection queue. While individual studies create an increased volume of studies, utilities in ERCOT have proven that these studies can be handled effectively if proper motivational incentives are in place. This approach also reduces facility study volume and backlog related to transmission owners, as projects could receive binding studies, but not be forced to move forward with the facility study until they were ready to proceed. The approach also balances interconnection cost with congestion and curtailment impact. It helps to align upgrades to improve as available interconnection service as contemplated in Order 2003. Lastly, this approach leads to high certainty for generators, which in turn allows for high milestone requirements to proceed. This slide is also shown by Hannes, illustrates interconnection results for a 300 megawatt wind farm requesting ERIS service on the SPP system. The project is in northwest North Dakota, but as can be seen in the graphic, multiple providers assigned upgrades over 300 miles away, some up to 1,000 miles. The restrictive criteria which caused these distant upgrades to be triggered are mentioned in shorthand and tend to involve either the collective impacts of a cluster or low TDFs and voltage change criteria. This slide highlights the importance of interconnection criteria being designed to appropriately identify constraints that are commensurate with the level of service requested. It shows the significant interdependency created by having restrictive interconnection study criteria and how queue processing can be dramatically slowed as a result. Without reasonable interconnection criteria, cluster studies will do very little to limit the impact of queue churn on interconnection queues. This slide covers a few related thoughts and suggestions on the Ferc GI NOPR. Regarding a non-binding optional study, many consultants can perform these informational studies without distracting transmission providers. There's a history of non-binding studies such as the PISIS and SPP and SPA and MISO, which show that interconnection customers still rush to the binding part of the process, even with high security and readiness requirements. This occurs because interconnection results are not dependable in the absence of knowing what other generators are in the cluster. The white paper recommends the individual impact study be required and used to identify local ERIS constraints. The cluster study would then follow during the regional study and higher service studies and allocate regional upgrades according to benefit to the generator and/or to the load. If the binding portion of the interconnection process starts with a cluster study, the initial study should start with only power flow analysis and short circuit ratio testing. Generators should be allowed greater flexibility for modifications to optimize the project once their cluster and initial results are known. For example, the pro forma allowance for 60% reduction and POI changes in sections 4.4 of the interconnection procedures should be extended through this first study, as is allowed by many transmission providers today. This approach shortens the initial study phase and avoids queue churn from withdrawal and re-entry by projects who are impacted by other cluster entrants. Additionally, Ferc should provide more specific direction on the degree of impact, such as TDFs, that a generator should have on a constraint, the types of contingencies to study, the appropriate fuel-based assumptions to use when requiring an interconnection upgrade. This would help clarify how interconnection service types should be treated in light of the ERIS and NRS products that Ferc has designed. There are currently high utility-initiated proposals being circulated at both SPP and MISO to lower ERIS TDF criteria in order to assign more upgrades at greater distances to ERIS interconnection requests. As presented in the white paper and these slides, Enel believes that improved regional study processes, particularly economic studies, more accurately justify the need for transmission upgrades and assign costs to beneficiaries of the upgrades. The next section of the proposal includes two key parts: commitment to regional study entry and the kickoff of engineering, procurement, and construction activities. We'll cover project entry requirements first. A key thought for readiness and financial requirements is that the risk for an IC to proceed should be commensurate with the certainty of the results that have been provided. Today's paradigm of high security requirements is tolerable absent exorbitant interconnection costs. In Enel's proposal, high financial risk and readiness requirements are borne by the generator in exchange for high certainty. High readiness ensures the regional cluster study is not bogged down in restudy. While not all upgrade costs are known at this point in the proposed process, any remaining upgrade costs come with a commensurate financial benefit and are not basic interconnection service upgrades. This slide covers a few thoughts and suggestions related to the Ferc GI NOPR. Regarding commercial readiness, a key point is that no generation project is fully developed and ready without binding interconnection results. Interconnection costs and schedules are a fundamental part of development. Where they still exist, transmission credits do significantly mitigate the cost impacts of interconnection upgrades to generators. However, the selection of a generator that does not have interconnection results in the solicitation process may lead to load reimbursing the generator for high transmission costs through transmission credits. Either way, selection of a generator before interconnection results are known poses significant financial risk that may result in suboptimal generators being built. Signing a PPA or bidding into an RFP without knowledge of interconnection costs and without schedules will result in broken contracts, generation capacity shortages, unmet customer needs, and/or high transmission costs to load. Regarding financial security best practices, financial security amounts should be based on the interconnection results to incentivize the withdrawal of projects with poor results. Withdrawal penalties should also be tied to actual harm to other projects, and forfeited funds should be directly applied to offset the specific harm to other interconnection customers. I've listed a handful of other industry best practices on this slide as well. Under the proposal, alternative solution proposals, facility studies, and EPC processes would commence after generators meet the regional study entry requirements. This slide lays out a framework for an optional competitive process, which would change the facility study into a competitive bidding process for standalone upgrades. We believe it would dramatically shorten the schedule and reduce the cost of both the facility study and the EPC process. The exact details could be revised to find the optimal solution. How would this competitive process benefit the interconnection process? Today, utilities have little incentive to reduce cost or accelerate schedules for generators unless they are contracting with the generator. Instead, utilities are often incentivized to drive up costs and delay schedules in order to obtain free land, discourage competition, and/or to increase profits under rate of return structures such as self-funding and transmission credits. For interconnection customers, the Good Utility Practice standard is virtually impossible to challenge. There is no effective oversight or cost controls from states or Ferc regarding appropriate design standards. Thus, utilities effectively have a monopoly position over interconnection customers for design, cost, and schedule of upgrades. Implementing a competitive environment with incentives and penalties for the winners creates a healthy balance where costs and schedules are improved. To illustrate the value of incorporating competition into the facility study process, consider these 3 switching stations, which are roughly at scale. Each station was built to accommodate a 345 kV line tap for a new generator. Each station contains 3 terminals and 3 circuit breakers. Note especially the significant size difference and the amount of bus work required in each. On the next slide, I make additional comparisons. For example, all substations start with the same ring bus configuration and are easily expandable to accommodate at least 1 additional connection. However, the last substation pictured requires 2.5 times as much civil construction work and materials and over 3 times as much bus work. Although this is not the result of a competitive process, these examples illustrate how there can be a stark difference in the design of upgrades. These images portray the vast difference in how something as simple as a 3-terminal switching station can be vastly overbuilt when proper controls are not in place. This slide covers a few related thoughts and suggestions on Ferc's proposal to eliminate the reasonable effort standard. While we don't enjoy the thought of this punitive measure, it is clear that change is needed. A few examples and statistics are provided from Enel's experiences in interconnection processes. This slide outlines 2 major adjustments to Ferc's proposed rules. The first is the competitive process described on earlier slides to provide motivation and penalties for transmission owners. It would also allow other companies to participate in EPC work, which would help with labor shortages. The second proposal is a recommendation that transmission providers should be required to produce a complete draft study report within the allotted study time, not a final report. This should be followed by a mandatory IC review period and then time for the transmission provider to adjust results and post the final study report. This will ensure that interconnection results are accurate and that all mitigation options have been considered before new security must be posted. Up to this point, we have covered the individual local impact study, the regional process commitment, and EPC kickoff. Now we shift to the third step in the process, a regional cluster study. The goal of this study is to calculate the potential benefits of the proposed new generators to load. The study would determine whether transmission upgrades are economically beneficial based on the value created for both the new generators and for load. As noted earlier, this study could be either a consolidation of the transmission planning and generation interconnection processes, or it could represent a new approach to interconnection studies. 2 of the key differences between this proposal and today's system impact study methods are the inclusion of an economic study and the sharing of transmission cost between generation and load. In this proposal, the transmission upgrades identified in the regional cluster study are primarily built by the load and for the load. Upgrades would be identified both for reliability benefit, including resource adequacy and TPL compliance, and also for economic benefit, reflecting load's access to new competitive generation. Rather than designing the grid with the limited view of exporting power from a single generator or a cluster of generators, the study would seek to capture the value that the new cluster of generation would add to load if adequately connected through transmission. Transmission upgrades would be built if the total value to generation and load exceeded the cost of the transmission. The upgrades would primarily be funded by load to reflect the benefits received, but generators would also contribute capital funds for the transmission commensurate with their expected congestion and curtailment benefits. Why is this regional cluster study approach beneficial? First and foremost, it identifies the most efficient transmission plan to provide maximum resource adequacy, reliability, and economic value. Transmission is built primarily by load and for load under this process, with contributions from generation commensurate with benefit. Under this approach, all parties benefit must exceed their cost or the transmission is not built. This slide covers a few related thoughts and suggestions on Ferc's proposal. As I've already discussed most of them, I will not comment on them again, but have included them in the slide for later reference. The final stage of our proposed interconnection process is to study higher levels of interconnection and delivery service, including NRIS, capacity interconnection, and transmission service studies. As a reminder, the initial stage of the individual local impact study would only study energy resource interconnection service. The premise for this proposal is that most transmission providers perform two distinct studies and grant ERIS as a basic service and NRIS as a more advanced service requiring additional network upgrades, though we recognize that this two-part study process is not always true. These studies would include unit-specific interconnection and transmission service studies. The studies would use more restrictive TDF thresholds and related criteria to expand the potential impact area consistent with the service type. The studies would also incorporate local and regional upgrades to increase the likelihood of reasonably priced service being offered, as the generator would be providing high readiness commitments prior to receiving these results. Generators would have flexibility to reduce their requested service amount to optimize the amount of service received and the associated benefits and revenue streams against the cost of transmission upgrades. The outcome of this study would be to increase generator-specific deliverability beyond what was economically beneficial for load to fund. This slide includes in writing what I described on the previous slide and is included for the benefit of those reviewing the slides at a later time. I will wrap up my presentation with the same slides I started with and share a few parting thoughts. So why are the reforms proposed today beneficial? First, new generation built with proper locational price signals and resource adequacy evaluation benefits load through increased competition, reliability, and environmental benefits. We must be careful to not forget the benefits that new generation brings to load. Well-designed transmission, coupled with competitive generation, reduces energy bills for customers. Today, transmission is designed very haphazardly through the interconnection process. Holistic and efficient transmission design should account for all expected grid changes and focus on the benefit to load. New generation faces tremendous financial risk in the interconnection process due to uncertain upgrade costs, high security deposits, and schedule delays negatively impacting projects. Some of the impacts of delay include loss of tax credits, missed opportunities for market participation, failure to conform to offtake agreements, and increased holding costs for development assets. The interconnection process designed in Order 2003 and subsequent orders is inadequate for the current volume of projects, despite numerous varied reforms attempting to address the issue. Clustering studies can help, but does not eliminate the project interdependency and restudies related to Q-churn. An efficient interconnection process that allows interconnection results to be known prior to committing a project to an offtaker is essential for proper development of new resources. This proposal would reduce interdependency, improve the speed of the interconnection process, and increase certainty for new interconnection requests. These improvements allow for more rapid construction of the generation that is needed to ensure a secure energy future for our country. As a reminder, please review these slides, the white paper at the link on this slide, and Advanced Energy Economy's ANOPR response for more information. I have included contact information for Adam and myself as well. With that, I conclude my comments. Thank you for your attention, and I look forward to the Q&A session.
Thank you, Aaron. And before you go, there are an enormous number of people on the call, and I want to make sure that everyone has a clear understanding. So very briefly, give us a 30-second, the difference between ERIS and NRIS, and what the acronyms are, and then just 30 seconds on the difference before we go over to Aurea.
Sure, there's about 20 years and about 40 different interpretations
okay, well, 30 seconds.
Answer that question, but in very brief, Energy Resource Interconnection Service, or ERIS, is considered by Ferc to be the very most basic interconnection service type that can be achieved when connecting to the transmission system. NRIS is a more advanced level of interconnection service that is meant to be comparable to receiving transmission service. Under the right circumstances, transmission service can be granted to a generator with NRIS without further study if the interconnection and transmission service queues are aligned closely enough. Is that helpful?
Yes, very much so. Thank you so much, Aaron. Thank you. Now I'll turn it over to Aurea Catanese, and he's going to continue the discussion with a look at some of the discrepancies between some of the interconnection study criteria. Horea? Horea, we can't hear you yet.
1 second.
Yep, I think we've got you now. There you are. Please.
You can hear me or no?
Yes. Yes.
Oh, perfect. Sorry, I was just asking if you can hear me. As I said, I was hotspotting. I'm on leave, so hopefully you guys can hear me okay. But if not, please wave at me and stop me.
We've got you now.
Awesome, amazing. Thank you so much. Well, hello everybody. My name is Horea Katanase. I'm a senior manager at EPRI. We're a consulting organization helping developers navigate the interconnection process throughout the US. With that being said, I'll kick things off. All righty. So this will be a three-part presentation. We'll start with some terminology and definitions, move on to dispatch methodologies, and then finish with a quick slide related to the recent NOPR released by Ferc. In today's presentation, given time constraints, we will primarily focus on MISO and SPP, and particularly on dispatch assumptions for the ERS and NRS studies. Some of the slides might look familiar to you guys if you've attended the previous webinar organized by ESIG, where my colleague Kalian, who helped me prepare these slides, presented. So yes, if those are familiar to you, there's a reason for it, but we needed them to make the presentation consistent. All right. So starting with the first part, we'll touch on terminology and some definitions. I think Aaron covered a few of the differences between ERIS and NRIS. I'm not going to read this out from the slides. I included a definition here from Ferc's website for your reference. But while these definitions can be a little bit of a mouthful or complicated, and as Aaron said, there's different interpretations of those things, I did like a recent definition that we heard from one of our colleagues who basically described it as ERIS gives you the right to connect to the power system, while NRS allows you to serve load, and NRS can also be important if you want to participate in the capacity market. Righty, next slide. I want to touch a little bit on fuel-based dispatch and flow gauge screening. Fuel-based dispatch involves dispatching various resources in accordance with the scenarios that they are studied under. For example, depending how you define light load, you might have different dispatches in light load, for example, for wind versus what you have for solar. Flow gauge screening is up next. And by the way, I'll go into more details in all of this when I talk about MISO and SPP, but flow gauge screening is up next. This might be a term that I think was coined by PowerGen, who are the developers of Tara, but it essentially involves dynamic dispatch of generators, whereby resources are redispatched in order to overload a particular flow gauge. So a flow gauge is a monitored element continuously pair, so that's what you can think of it. And there are many ways flow gauge screening can actually be done. You can have timers to reference, timers to helpers, etc. But the way it's done in MISO, and actually if you guys are interested in PGM as well, although I won't be covering PGM in this section, it's usually timers to reference. This involves ramping up worse armor generators and uniformly scaling down generators in the reference subsystem. There typically are other criteria of how we do flow gauge screening, so there might be some sort of a criteria about how we limit such generators. So there might be defects criteria, maximum transfers, number of generators, etc. And we're going to cover some of those as they relate to MISO in the following slides. This slide I thought was kind of interesting. I saw it in a MISO presentation. It kind of describes the different load levels that we see and how likely they are to occur. And this concludes the first section of the presentation on definitions. And we will now move on to the main section of the presentation, which covers cases using interconnection studies and dispatch methodologies. So starting off with a deep dive into SPP, I'm sure a lot of you folks on the call are probably aware that they have recently introduced some fuel-based dispatch into their interconnection studies and have also reclustered their groups. And more on that is to come on the next slide. First, I'll talk a little bit about the request types and cases used in SPP. So in SPP, interconnection requests can be studies for energy resource interconnection services, ERIS, and/or network resource interconnection service, NRS. All new projects must be studied for ERIS, but do not need to request NRS. The requests are also binary. What I mean by that is they either request full service or no service, which is different when compared to MISO, where you can request partial service, but we'll talk about that a little bit later. SPP runs thermal and voltage analysis for both ERIS and NRS requests. Prior queued, so PQ and current queued PQ models are created to study these requests, and these models are created for summer peak 2 years out, light load, summer peak and winter peak 5 years out as well. Think of the PQ model as the pre-current, we'll talk a little bit about this later as well, but think of the PQ model as the pre-current queued model, and the development of the models themselves are quite complex, as GI projects and any associated upgrades in neighboring systems such as MISO, MPC, etc., may need to be included depending on their relative queue priority. Let's move on to the next one. So again, request types and cases used. We'll talk a little bit more about the different cases that we have. For those of you that have attended Kalyan's presentation, again, this slide might be quite familiar as he touched upon it, so I don't want to spend too long on it, but I do know we have quite a few new attendees, so I will go through them. So HVER dispatch reflects scenarios in which variable energy resources are generating at high levels and conventional resources are at the relatively low levels. HVER scenarios are developed for summer and winter peak and light load seasons and evaluate both ERS only and NRS requests. LVER dispatch reflects scenario in which variable energy resources are generating at low levels and conventional resources are at relatively high levels. And then NR dispatch reflects scenarios which NRS generators output is maximized and ERS only generators output is minimized. NR scenarios are developed for summer and winter peak and light load seasons and evaluate only NRS requests. Note that while a number of different scenarios are simulated, the dispatch itself is static during the simulation. So basically, if you remember the first section in the presentation, we're not talking about flow gate screening here. And again, we will see that a little bit more of that in the next slides and tables. So the SPP grouping, again, I just wanted to give you a sort of visual of the groups that we have in SPP. So the reclustering of SPP groups and how these have reduced from 18 to 5. The 5 current groups are SPP North, North Central, Central South, Central, Southeast, and Southwest. Apologies. All righty, so let's talk a little bit about case development and dispatch assumptions. So the starting part is the integrated transmission planning, the ITP base case, and which is the starting point for all of those models. Once applying fuel-based dispatch to maintain balance, online generators within SPP must be dispatched per the below. For HVER and LVER scenarios, additional generation is offset by reducing this dispatch of ITP generators across the entire SPP footprint based on load ratio share of the TO power flow modeling areas. And I know I'm introducing kind of a new concept here, which is the load ratio share, but I will cover that in subsequent sections. So there we are here. I've kind of, the slide contains details about how the load ratio share is performed. You can refer to this slide for all relevant details, but I'm going to try and simplify the concept. So load ratio is effectively the sum of the area load divided by the total system load. As we ramp up generation, obviously we need to ramp down generation elsewhere to maintain system balance, and we're doing this in SPP using this load sharing method that is described on this slide. Now, this next few slides are going to contain some tables about the HVER, LVER, and NRS dispatch. And again, all of those are fuel-based dispatch dispatches. So if you remember, we defined fuel-based dispatch at the beginning, and the concept behind it is to allow for stress cases which are supposed to resemble the generation conditions observed during each loading scenario. Again, we've described that SPP is broken up into 5 regions and groups. So if you see there on the slide, in-group refers to the queue projects in the same region as the group under study, while out-of-group refers to the queue projects outside of the region. PQ refers to prior queued requests that have not been included in the ITP-based reliability model, while current queue refers to the current queue. NC means no change in the dispatch from the integrated transmission planning model, while NA just indicates that it's not applicable for the particular scenario. The percentages that you see there in the tables are based on requests to the Megawatt interconnection services. Now, I don't want to confuse people, but please do note that there is some more complexity associated with prior queue and current queue, as there are some scenarios wherein a prior queue project may be considered as a prior queue exception. For example, when an in-group prior queue generator has an electrical equivalent POI as a current queue project. Again, previously discussed, for HVER and LVER scenarios, the increase in generation is offset by reducing the dispatch of ITP generators across the entire SPP footprint based on the load ratio share of the TO power flow modeling area. So with that being said, I'll leave here next slide. I'll leave here the Nrs dispatch example. Again, very similar table that we've seen in the previous 2 slides. Again, I'm not planning to go through this in detail due to the time limitations, but here, if you want to reference back, there's a hybrid example, so how hybrid projects are treated for this particular dispatch. And this pretty much concludes our SPP section. Hopefully, you're still all with me. So I'm going to try to quickly go through the MISO side as well. Again, same thing here. We're going to go through the request types. So in MISO, developers can request ERIS, NRIS, and partial NRS, as we discussed. MISO also runs thermal and voltage analysis for ERS requests and a deliverability analysis for NRS requests. Deliverability analysis is based on flow gauge screening, which again we've covered at the beginning, and I will provide some more details on subsequent slides. Bench, like the PQ model in SPP, and study cases are created for the ERS analysis based on 2 loading scenarios. Summer peak and shoulder in this case, and NRS model used in the NRS model used is based on a summer peak loading scenario. So ERS cases and dispatch, again, for ERS similar to SPP, fuel-based dispatch is used to develop the cases. First, MISO MTEP models are used as a starting point, and existing generators and generators with a sign IA are dispatched based on the MTEP 5-year out local balancing authority dispatch. We'll give you some more details on that on subsequent slides. For the bench case, DPP higher queue projects without a GIR added and dispatch based on a fuel-based dispatch. Similar to SPP, I've included some tables in the following slides. The study case includes all the current DPP projects, which are again dispatched based on fuel-based dispatch. Again, it's worthwhile noting that rather than using a load ratio share in MISO, any increase in generation is rebalanced by syncing in MISO Classic or MISO South, depending on the location of the queue projects. NRIS, as I've mentioned, it's based on the ERS model with upgrades included. ERIS-only generators are turned off, while NRIS generation is set up to at least PGN equals to 0 and available to be ramped up. ERIS generators with firm transmission are treated as NRS. And again, as we discussed, those NRS units are ramped based on flow gauge screening. So the algorithm will have a defects cutoff of 5% and a cap of 30 generators, but it's very important to know that it excludes the current DPP cycle generators. There's also an 8,000 megawatt cap on additional generation to be ramped up. How does this work? The algorithm ranks eligible generators contributing to each flow gate in terms of their defects and dispatches them from the highest to the lowest until the cutoff is reached, any of the cutoffs. And to compensate for this, the rest of MISO system is uniformly scaled down depending on location. Again, apologies for that sound. Now, I've very quickly wanted to cover some of the 5-year out LBA dispatch. So hydro is dispatched at a 5-year seasonal average, renewables dispatched to seasonal levels or capacity credit levels. The dispatch algorithm will maintain area interchange, and firm resources are dispatched by LBA tier order, which is kind of a pseudo economic based dispatch. Same as with SPP, I kind of wanted to give you an example of how this is done. So this is from MISO's BPM manuals, it's in manual 15, if any of you guys are curious, but I'm just going to leave this here for you to, as kind of like a reference. Now, before, you'll be happy to hear probably that I only have one slide left, but before I move into that, I just wanted, I want to recap a few things. We've looked at different dispatch methodologies and how they are applied across two major RTOs. Now, it is important to note that the ramping and sinking of generators under study is not based on an economic dispatch model. And, this may lead to a few questions. For example, in flow gauge screening, what is the probability that the top 30 worst contributors to constraint are all online, plus all the study generators at the same time? Could this potentially lead to expensive upgrades? Can we manage some of these less likely cases through curtailment, more closer to what ERCOT does? How do you balance the need for building necessary transmission infrastructure versus preventing backlogs and integrating renewables at the rate that we need to in order to achieve our clean energy goals? If we were to do a pure economic dispatch, are some of these details confidential, and could they be included in a public model? I'm not sure. Again, also, like, those cases are 5 years out, so could we accurately predict things like fuel prices? Maybe, maybe not. Those are all probably interesting questions that I don't think they have necessarily simple answers, but I kind of wanted to leave you guys with some thoughts to sort of ponder on. And with that being said, I'll move on to my very last slide. This is just covering some of the stuff that came out in the recent NOPR. I wanted to quickly run through some of the things discussed in this. Most of the focus was on hybrid projects and storage and how potentially unrealistic assumptions can lead to unrealistic upgrades. The proposal does mention the transmission provider should use operating assumptions for interconnection studies. That being said, the proposal also does include a provision which allows transmission providers to hold interconnection customers to the intended operation of their plant. Also, the NOPR 6 comments on whether the commission should do the following three things: expand proposal to tackle transmission providers, studying scenarios that are not typically possible, define the peak load period. How do we define that across different regions? That's probably not easy because different regions define it differently, and whether or not we should define firm and non-firm charging and require defined study criteria. I think I managed to finish it in time, but that's pretty much me done.
Excellent.
Over to you, Warren.
Excellent. Thank you, Horia. I'd ask the other two panelists to join us back on screen, if possible. I have some questions here. There we go. Aaron, great. Okay. So first of all, thank you all three for excellent presentations. I do have some questions here that are, some of them are actually my questions, and some of them are kind of consolidations of some of the ones on Slido.com. So there, I think two of the kind of trends, issues that are being asked in many of the questions on Slido. The first is associated with cost allocation. I am curious, generally, the three of you, I'm curious what your thoughts are on to what extent are the current issues that we are seeing in the interconnection queue study process, to what extent is that kind of some of the reliability studies, the physical studies getting wrapped around the axle of cost allocation? I'm especially interested in that one example that was given about the upgrades far, far away from the unit. Thoughts?
Yeah, no, Warren, this is a very good question. Ultimately, cost allocation is what matters because somehow somebody has to pay for either the transmission upgrades or the higher or lower generation costs that are associated with upgrades or the lack of such upgrades. Generally, the idea is that beneficiaries would want to pay. So if the beneficiary is primarily an interconnecting generator, it makes sense that the interconnecting generator pays for a portion of that. But we have to also keep in mind that these generators that interconnect ultimately have customers, and the customers will pay for those interconnection upgrades. So my approach to this is the first thing we want to do is reduce the total costs in the system. If we can manage to interconnect generators for a third of the cost that are caused by the current processes, cost allocation becomes much easier. The more cost effective the solution, the easier it is to allocate costs. I think a lot of the interconnection problems that we have right now is that the study criteria trigger very expensive upgrades that are allocated solely to the interconnecting generator. So the combination of inefficient upgrades with 100% cost allocation to generators creates the churn that we have in the queue and the problems that we have to start out with. So we need to find a better solution, and it starts with getting to more cost-effective solutions before we get too worked up over cost allocation.
Understood. Aaron, Horea, thoughts?
Well, do I go first, Aaron, or?
Sure, go ahead.
Okay, sure. Just to add to Hannes' point, I think it's also an interesting one with how much visibility you have into cost allocation, especially when you're talking about affected system studies and stuff like that. At what point in your process do you know exactly what cost allocation you have? What happens when you have a lot of withdrawals? That changes. Does that lead to projects staying on in the queue longer for, kind of in the hope of getting through? I think Hannes made a lot of good points. I just kind of wanted to add that on top as a different perspective too.
Yeah, likewise. Hannes definitely did a great job describing a number of the issues. One thing I will say is cost allocation generally has two different flavors. One kind of flavor of cost allocation is when you're directly talking about cost allocation and you say, here's the upgrade we need to build, now who pays for it? The other type of cost allocation that comes into the picture is all of the study assumptions and criteria that are built around the interconnection process and transmission planning processes that not just say who pays for it, but what are we even identifying in the first place? So I mentioned, for example, in SPP and in MISO, there are current initiatives to try to reduce the transfer distribution factor threshold from 20% to something lower, maybe 10% or 15%. The net effect of that is it creates more upgrades in the interconnection process that ultimately results in more cost being allocated to the generator under today's paradigm. So again, there's kind of two aspects to cost allocation that, in my mind, when you really start diving deeply into the thick of all of the theory behind interconnection processes, almost every decision, almost every study assumption, it's all tied back to cost allocation in one shape or form. So it definitely is kind of deeply involved.
Yeah, excellent, excellent. This may be more of a kind of just a process question. Jorge, you may be able to cover this best. You hit on this to some extent in your presentation. So if someone is interconnecting let's say a wind unit, and the interconnection studies are being done, what are some of the assumptions associated with the dispatch level of some of the units right around that unit? Is that kind of different from the regional, or give us some understanding of how the units nearby an interconnecting unit are considered in these studies?
Sure. I mean, I think it's a simple question that it probably has a little bit more of a lengthy answer. I think it depends where you're in. It depends what type of study you're doing. So let me try and cover at least maybe a little bit SPP, MISO. Maybe I'll give a quick flavor on PJM as well, since I haven't really covered it during my presentation. If you're talking IRIS, in MISO, everything is fuel-based dispatch, right? So it will be this. All the study units will be dispatched at the levels that are described in the tables that are provided in my presentation.
Right.
And everything else, right? So everything that has a fine GIA will be based on the transmission planning dispatch that's sort of sort of economic based. If you're talking NRS and ERS in SPP, they're fuel-based dispatch. If you're talking NRS in MISO, you have that flow gauge screening. So the idea of it would be let's say you have a particular constraint, you're trying to maximize the flow through that constraint by ramping up generators. And all the nearby generators, if they're very close together, the chances are they would be all harmers to that particular constraint. So you're ramping them up to the maximum and trying to create quite an onerous dispatch. To touch a little bit on PJM, PJM also has a flow gate screening based approach. They are changing it, so I don't want to get into that. But that in PJM, whether you're putting a capacity or energy request, and I know the terminology is different, and I apologize for that. Probably no time to explain it. But it's also based on fuel-based dispatch. And right now, how those, on flow gate screening, not fuel-based dispatch. And right now, how that cutoff is made depends on the type of contingency that you're studying, among other things. But it really does depend from area to area, so it's kind of hard to give you an answer that includes everything, which is part probably of some of the challenges that we're facing.
Very much so.
I don't know if anybody else want to add anything to that.
Yeah, any other thoughts?
Yeah, I'll dive in for a moment. One of the questions that I think fundamentally underlies the question of dispatch. So if you're talking about, say a wind and a solar plant or a wind and a gas plant that are located in a similar area or even in more discrete areas of the grid, really one of the fundamental questions we need to ask is whether it is an issue that needs to be mitigated through upgrading the transmission system, or whether it's an issue that should be handled through market and operational mechanisms, or said another way, through congestion and curtailment of the dispatch units. That is one of the places where I, for almost my entire career, have really felt that power flow modeling falls short in. Power flow modeling really only captures a few very discrete specific points in time and does not really capture the breadth of a full yearly dispatch of a unit. So you're seeing that there could be a potential constraint on the system, but what it doesn't tell you is whether that constraint exists 1 hour of the year or 8,000 hours of the year. And depending on the answer, really changes your value proposition in whether it makes more sense to be upgrading that line so that your generator regularly can inject power, which is what I kind of view as the as available moniker that Ferc used in Order 2003, or whether we should just allow those generators to self-curtail through market mechanisms to ensure that the grid remains reliable that way, because both are valid ways to keep a reliable grid.
Okay. Hannes, anything to add or move on to the next question?
No, one thing I want to say is, as we looking at clean energy standards, the objective is to get more clean energy onto the grid. The interconnection study processes are inherited from a time when it was all about capacity, getting capacity on the grid. So I think, as Aaron said, when it comes to energy, it's really the headroom that exists in 87, 60 hours of a typical year, not the 1 hour during peak load conditions on N-1 contingency that we might need for capacity type reliability. So I think we need to do a better job distinguishing between energy interconnection study assumptions and capacity interconnection study assumptions to make this all work in a more cost-effective way.
Yeah, very interesting. Okay, shifting a little bit, there's a question about the speculative nature of units in the interconnection queue, and how do you handle that if you're shifting some of the studies to non-interconnection studies? How do you address the speculative nature of the units?
Well, there are two challenges with that. One is short term, like what will actually interconnect in the next 3 years. And that I think can be addressed through more sort of a first ready, first serve kind of approach, that unit that don't make progress in permitting or so on are put at the end of the queue, and the units that can actually develop, that have site control, that can be built, will be first served. But this question often comes up in the long term, like how can we possibly plan for 2030 or 2040 if we have no idea what gets retired and where the units will be added, or whether it's wind or solar or something else. And that's where long-term scenario-based planning comes in. So if we look at the MISO MVP, the multi-value portfolio that they just put out, that is a least regrets portfolio that works well in almost every plausible future. So you have to look at different plausible futures to deal with the uncertainty, and then come to a least regrets build out that either makes sense in most futures or ensures against extremely high cost outcomes of not when you don't have a robust enough grid and really wished you would have done something about it earlier.
Aaron, Horia?
Yeah, I can offer a kind of a developer's perspective on that. From a developer's perspective, really every generator is speculative until you have interconnection results. So that's one of the fundamental things that I think a lot of people don't always recognize is until you know the cost of your interconnection, which can make or break a project, every project entering the queue is speculative. That being said, Enel has long supported good, healthy development requirements and readiness requirements in order to enter the queue to show a reasonable effort towards proper development of that project. Site control in our minds is one of those really core fundamental things, and Ferc has proposed that as a requirement across all regions, and we agree with that. There are other requirements. I think I noted in my presentation, we really don't think the commercial offtake aspect of that is the best use of readiness requirements. But really showing that you've made significant progress, that you spent significant money on various aspects of development of that project, that really is important. And then as far as the kind of the aspect of the question about how do you do regional planning well, knowing that not all of those generators are going to ultimately succeed, one of the things I point to is that regional planning largely should focus on a lot of the backbone issues. So the really core trunk line highway system type upgrades. And then the individual generators can focus on local upgrades that will allow them to access that higher voltage system. The MISO MVP projects, I think, were mentioned a couple of times. That is an excellent example of an RTO looking at where is the resource strong and then building a transmission system that accommodates those good resource zones. And then it was followed by the subsequent development of local projects within the vicinity of the trunk, kind of the trunk line upgrades to the transmission. So.
Interesting. Horia, something to add or?
Very quickly, I know we might want to get to one more question, but I think, again, Hannes's point about MVPs and RNs as well in MISO, I think that's a great one as well with the first ready, first served approach. I think that's getting more and more popular. I think, you know, the readiness deposits that are introduced that are partly refundable in a few of the different ISOs that may deter some of those very exploratory projects. I do see Aaron's point though, until you kind of see cost, maybe everything is exploratory. But I think some of the RTOs are, like, again, PJM is moving to a first ready, first served type approach now, and very kind of similar to what MISO's process are, but that should at least hopefully reduce some of those speculative projects that we're seeing.
I mean, one thing that we haven't addressed right now is it would also help dramatically if the regions would let developers know where headroom exists or where it could be created cost effectively. So you guide interconnection requests to those portions of the grid that either have good resource potential, like wind and solar areas that can be developed, or where that's just you have enough grid. I mean, we know if PJM already knows that we need to interconnect 75 gigawatts of renewables over the next decade, we might just as well give people a sense of where the best locations for those renewables might be in terms of existing headroom or headroom that can be created at low cost.
Interesting. So I do believe we've got time for one more question. Near and dear to my heart, having spent a good bit of time at ERCOT, kind of the idea of ERCOT and Great Britain. Any thoughts about why those processes seem to be able to move projects through the queue quicker? Just kind of thoughts on that.
Well, I mean, Aaron knows the most about some of the differences. Do you want to start on this one, Aaron?
Sure, I can jump in. And so I will caveat this by saying that I am not an ERCOT expert. I do understand the process at a very high level, and I have a bunch of people on my team who really are what I would call the ERCOT experts.
Yes, you do.
But at a fundamental level, really the main reason why ERCOT's interconnection process is so fast and so effective, I think really boils down to two things. One is that there are no upgrades assigned to the generator at all. Not only are they not cost allocated, but they just don't build anything, period. They build your connection facilities to physically connect you to the grid, and nothing else is built as a result of the interconnection process. So you have no interdependency, you have no Q churn, you don't care about withdrawals because even if someone withdraws, it doesn't affect anyone else because there's no upgrades that are being depended on. The other aspect, I think, to why ERCOT's interconnection process is so fast is because the utilities there, all of the upgrades, all of the points of interconnection, all of that is billed to load and is rate-based. And so all of the utilities are able to earn a rate of return, which is, of course, a very healthy and safe rate of return on their investment in those upgrades. And so utilities are generally very motivated to complete the studies and to connect your project because it's a profitable endeavor for them. That's not necessarily the case in all regions of the country. So that goes back a little bit to the competitive process I described in some of my slides, is that you provide incentives that motivates the utilities to be a part of the process instead of being arm's length opposed to the process.
The one thing I would add about ERCOT, and it's sort of similar in the UK, connect and manage allows generators to connect quickly, but they also are then managed in how much energy can get on the grid. So the generator, if they interconnect at the wrong location, they're exposed to much more congestion management, curtailments. And I think that's actually a good price signal because it does make interconnecting at the better locations on the grid more valuable. But you don't require all the upgrades to get built before anybody is allowed to interconnect. And then the complaint I've heard about ERCOT, Warren, is that the transmission planning process is then sometimes too slow to address high congestion costs and curtailments.
Yeah, understood. Aurea?
Again, I'll try and be brief because I know we're kind of out of time, but yeah, it's really a different game, I suppose, in ERCOT, right? As Hannes mentioned, it's about congestion and curtailment rather than network upgrade, so you have to pick the right location from that perspective. By the way, it's kind of interesting. I'm from Canada. I don't think I mentioned that at the beginning, but ASO in Canada has a kind of a similar approach. I think they allow RAS schemes as well in there, but yeah, I think it's more of a game with the congestion and curtailment rather than looking at network upgrades.
Interesting. And I would add moderator's discretion here. I would add building in the wrong place. I think Hannes said what is being found in ERCOT increasingly is the role that stability constraints play in some of the curtailment issues. And many of those stability constraints are not identified until very late in the interconnection study process. And so I think that may be another dynamic that kind of is felt more and more across the rest of the country. So that's something to look out for. Please, I know we can't hear the applause across the internet, but please help me thank the panelists today for excellent presentations and very interesting discussion. And I will turn it back over to Julia. Thank you, panelists.
All right. Thank you so much. That was great. Great session. We now have a break for 7 minutes, and we'll resume in the next session. Thank you.
Hi, it's 12:40. Hopefully people are back from their break. I'm Debbie Liu. I'm the Associate Director of ESIG, the Energy Systems Integration Group. And welcome to session 2. So this morning we had some great presentations. We heard potential solutions to the generator interconnection process, looking at reducing scope of generator interconnection processes so it doesn't trigger deep network upgrades. That should be part of the transmission planning process. We looked at coordinating siloed transmission pieces, such as generator interconnection, local and regional reliability, and regional and even interregional transmission planning, and finding least cost solutions to this coordinated, integrated process. So now we're going to dive into examples. And the first example is going to be by Matt Pulaski and Sunny Rahim, who are going to be discussing SPP's new consolidated planning process. I'd like to remind you that if you have any questions, please go to slido.com, enter in the code ESIG9, capitals ESIG, and then the number 9, and enter in your questions, and please vote up questions so we can ask them in the discussion phase. And I'd next like to introduce Matt Pulaski. He's the Executive Director of Business Management and Regulatory Affairs at NextEra, and Sunny Rahim, who's the Supervisor of Modeling at Southwest Power Pool. So Sunny and Matt, take it away.
Great. Thank you very much, Debbie. Really appreciate the intro. I'm going to kick things off here and then turn it over to Sunny, and then we'll tag team the rest of the presentation. Before I start, I did want to say that I think if the participants were on the earlier session, there are so many parallels to what we're going to talk about here. And it's great to hear Hannes, Aaron, and Jorge talk about the need for better planning and for more information to go into the planning phase. Because that's essentially at the end of the day what we're trying to accomplish. And I was following some of the questions earlier about workload and about how to integrate data and about all these great questions that can improve the planning process. And I think that that's exactly the challenge that we're taking on here in SPP. So it's just I really appreciate the last few presentations, but I think again there is a great segue to what we're going to talk about here today. So as Debbie mentioned, I'm Matt Pulaski. I'm the Executive Director at NextEra Energy Resources. Have a lot of work in regulatory, but also in interconnection for our projects around the country, but primarily in SPP and MISO. And I'm also a very proud member of the Cpptf at SPP and have been since the initiation of it. So we love our acronyms in the electric industry. So again, what we're going to talk about is called the Cpptf. What it stands for is the Consolidated Planning Process Task Force, and we're going to give you kind of an overview of what we're doing. It's a work in progress, but a lot of good ideas already coming out of it. So again, talking about acronyms, the Cpptf was originated from what SPP took on as called Cpptf. Script is the strategic and creative re-engineering of integrated planning team. That probably takes the icing for the cake for the greatest acronym in the electric industry, in my opinion. But what the effort was, and we'll talk about some of the recommendations in a second, what the script effort was really all about is looking at the challenges that are facing SPP, primarily in a lot of the planning areas. Which includes generation interconnection, which is why it's so relevant here, and how to look at solutions, but not just look at kind of really easy solutions, but to kind of look across the board and say, can we really re-envision this process? And how do we do that? How do we do that both from a more like, easy picks ideas where we can kind of implement them right away, but also some of the larger areas that we can focus on. Cpptf originated from this effort. I would say that it's probably one of the longer term efforts in there, but I think one of the most important ones. And I think the important thing is that both the script effort and also the Cpptf, the makeup of the people on those efforts included not only board members and SPP staff, but a complete list of stakeholders across the board. So whether they were utilities or developers, regulators, others have been involved in this to come up with this process. So again, one of the bigger areas that we focused on was the planning challenges, and no bigger than with the large Q and SPP than the generation interconnection process. Cpptf, relatively new. It was formed by the board of directors in late 2021. We've had a dozen or so meetings led by Sunny, who's the staff lead for Cpptf from SPP staff, and a lot of really good work so far, focusing on let's learn the current process. Like, let's learn all the different things that we're involved in, and Sunny will get into some of that as well as we move through this. So again, going back to script a little bit because it sets the stage for how we got here so far. The recommendations that are really focused around the planning processes for script focus on really three big areas. One was, and Hannes mentioned this, so did Aaron, and so does Horea as well, the large queue. Right? SPP has an abundant resource of renewable energy and also has one of the largest and longest queues in any RTO ISO. How do we focus on improvements of that process? How do we look at that differently? And along with that, because it's not just planning for GI, but also for some of the other areas. So for example, long-term transmission and what we call attachment AQ, which in SPP is delivery point load additions and subtractions. So that was certainly one big area. But then it didn't just stop as, how do we mitigate it, but how do we actually improve it? Right? How do we get the process to be different? And again, I saw one of the questions in the previous presentations about how do we take this workload off of these engineers in the GI process or the planning process that are already strapped for time? They're already overworked. They're already, in high demand in the industry as well. So how do we work smarter and better rather than just kind of grunt through the opportunity? So streamlining and optimizing planning is certainly a big area. Cost allocation was certainly mentioned a lot in the previous presentation as well. It is a large focus of ours. We're just starting to get to those discussions in the Cpptf, but the script already thought about that ahead of time and said, look, at the end of the day, if we have better planning in SPP, it also has to come with a better cost allocation, cost sharing proposals, right? And Aaron threw out a bunch of different ideas, TDF analysis, voltage analysis, other areas that are aligned with cost allocation. That is all on the table with our CPP effort. So a little bit about the scope of the Cpptf, the task force that we're working on. So again, really focusing on how do we rethink all these processes? How do we rethink what assumptions are used? How do we rethink what data comes in and out? And really kind of envisioning what's the best outcome for SPP as a region and for all the stakeholders in that region, and how do we best implement it? So that includes a lot of different areas. And again, Sunny will get into some of those areas in a second. But it doesn't just come with like, what are the ideas, right? It has to come with how do we actually implement them? In SPP, we have something called revision request, relatively common term, but it's a term for if we need to make changes, let's make the changes, whether it's in the tariffs or the market manuals or anything else like that. And if it has to go to Ferc, let's think about that ahead of time so that we can properly implement those. And then in SPP, we also have many working groups, transmission working group, market working group. These are all stakeholder-led groups with staff support on them that come up with a recommendation. So how do we engage those groups? Many of the members of the Cpptf are also members of those working groups and have been tremendously engaged in a lot of the discussions, which is really encouraging because they bring their expertise to the table to say, how should we approach this? How should we improve this specific area? And then also really identifying what can't be done potentially, right? What's potentially not going to be able to be finished, especially with the timeline that we're on, which is just a few years, as we'll get into in a second. So that's a little bit about the scope of the Cpptf. Again, it's a very large effort. And at this point, I'll turn it over to Sunny to cover some of the specifics, and then we can tag team the rest of the presentation.
Yep. Thank you, Matt, and definitely want to thank you for including SPP in this agenda topic. It's very well suited based on the discussion I heard this morning, and a very good opportunity to raise awareness across the industry on the efforts that we are taking on as SPP and our stakeholders. I think it's a great investment and commitment shown by our organization on coming up with a more holistic approach to doing transmission planning. So currently in the SPP planning processes, we have several parallel streams that are focused in on particular scopes. So we have the generator interconnection process. You heard the presentation earlier today detailing the requirements of that process, and that's looking at new interconnection or modification of interconnection resources on the generator side. We have the integrated transmission planning process, which is our regional planning processes, looking at public policy, persistent operation issues, and forecasting different future assumptions into the regional plan. Our interregional planning process, this is where the JTIQ process is joined at, and this is also our relationships with our neighbors on planning across the seams. Balanced portfolio and high priority, these are our EHV looks at a regional need. So if we have a change in scope or change in the future, we use these mechanisms to help us plan ahead of time for those needs. Sponsored upgrades are a study process that allows an entity to propose a transmission or network solution, and we'll evaluate that to see if there's any adverse impacts or any additional constraints to the SPP system. Transmission service, this is your long-term transmission service queue, and then load addition is your attachment AQ for delivery point modification process. So you can see just on this slide, there's several parallel dots. They could all encourage different opportunities to modify scope, criteria, or cost allocation opportunities. There are advantages of running things in parallel. The most important is probably some of the parallel processes could be performed quicker than others, and they don't have to wait on the complete studies from the other processes to complete. But that's something that we feel like we can accommodate through our CPP design development. We've broken it out into two different phases. The CPP process, what we're really focusing in on is clearing the backlog for the generator interconnection queue we have at GI. This has been a Ferc filing that was approved, and happy to report we're well underway with clearing the backlog here at SPP and on schedule. We believe that's a first critical step in setting up the successful foundation for a consolidated planning study. The next most important piece is being able to collect data and correlate data efficiently across all of our planning needs. This ranges from NERC standard data collection from GI customers, load addition customers, and our regional planning studies. So we've communicated and gotten endorsement from our board and stakeholders to commit to improving and being very innovative with our automation needs as part of this CPP development process. One other idea that I really like that I heard earlier, scenario-based modeling. Right now we build several common model sets. One model set for GI, another model set for long-term service. So each parallel process probably has their own common model set that's being developed. The recommendation here is to centralize assumptions, centralize modeling reporting requirements, and build one common set of models that cover our reliability needs from a steady state, short circuit, and transient stability, and economic needs assessment. So centralizing all that into one synchronized model build is going to help us be more efficient with our time and provide consistency across all of our planning processes. The next recommendation under the Cpptf is to better correlate service products into our regional planning processes. You can see this highlighted in the Ferc NOPR as a requirement that's being proposed. You can hear stakeholders throughout the industry championing for this inclusion, and we've already captured that as part of our recommendations to work towards. The last two recommendations are about cost sharing. It's really bringing load serving entities and service customers to the same table and identifying the right amount of certainty to provide on the front end of the assessment, and how are we going to share costs when it comes to cost assignment and cost sharing. The most optimal upgrades are going to require all of us to be at the same table to make those decisions. And the last one is schedules. So when I think of schedules, I think of what gives us enough certainty and provides us the right duration for us to provide our customers the right schedule to make decisions, their own business decisions on. And right now, that's following our integrated transmission planning schedule, our ITP schedule. So those are the recommendations kind of in a nutshell that we're working on. We've got these recommendations at a 30,000 level and trying to break them down into policy direction for our organization group to implement. So just an illustration on how the parallel processes currently work at SPP. You can see on this slide that we have several parallel processes. You have the generator interconnection process, which has the SPP impact assessment process going on at the same time an affected system study could be going on. There could be opportunities for service customers in that process to withdraw at any point, triggering restudies. We also have our regional planning studies going on, and these overlap within their own study schedule. We'll kick one ITP off, and then a couple months later, we'll start scoping the next one. And then you can see our regional planning processes are occurring at the same time, and transmission service products are occurring at the same time. And it's really a race to the finish for cost assignment right now. What we'd like to move to is on the next slide, which is consolidating all of these requirements into a coordinated open window for submission of requests from the service type, scope development for the regional study, all occurring at the same time using common models, whether that's scenario-based or other means of modeling different types of dispatch, and having one large annual study that encompasses all of our regional needs: generator interconnection, transmission service, load addition, local planning considerations, and our responsibility to the NERC reliability standards. We are trying to target a design completion by third quarter of next year with implementation by the close of 2024. We realize that there are some processes at SPP that occur quicker right now than our ITP study, which is a 24-month study, and those would need their appropriate on-ramps and off-ramps incorporated in phase 1, or they may have to be moved to phase 2 to better design the process to fit those quicker turnaround studies, like our AQ, which is our delivery point addition study, generator retirement process, or sponsored upgrades. So we do have a phase 2 designed. I also like the breakout of phase 1 to phase 2. There's several Ferc NOPRs out there, and as they progress the orders, we will have the opportunity to determine if they fit into the phase 1 development or phase 2 development. So what's the benefits? We've discussed these at length earlier in the presentations, and what we are really trying to achieve under the Cpptf effort is timely and accurate planning studies. We're trying to put all of our assumptions together at one time in an annual study and build the best, most cost-effective and holistic transmission solutions, reinforcements that could provide benefit to multiple types of customers. This is also to create consistency in criteria, cost sharing, and also helps us be more efficient with enhanced automation and technology needs. And then as the process evolves, we're going to identify a lot of benefits in doing this coordinated study, not only just the most holistic transmission solution, but there will be benefits that are underlying that we'll realize later. And the biggest benefit, one of my personal favorite, is at the end of the day, we should be finding solutions that are more cost effective and reliable and really are benefiting our ratepayers.
And if I can just add, Sonny, I mean, I think that, again, tying some of the previous presentations to this, we think that doing these studies on a more consistent basis, almost on a rolling basis from year to year, by including all the right data, by making sure that that data is correct, that it fits the right scenarios, what we're doing essentially is doing ongoing planning as information's constantly coming in. And that's the end goal, because if we can do that, and if we can get those studies so that, like, for example, generation interconnection data is coming in, the studies on the generation interconnection side take maybe just a few months instead of a longer period. We're constantly doing planning for those new generation interconnection requests or delivery point requests or generation retirement, for example. And our thought is that by doing that, you are putting projects in place to meet that demand in as close to real time as you can. And I think that that's ultimately what we're trying to get to. But I also think that that's going to be the end result for a lot of the processes that were discussed earlier. But we have to have the structure put together properly in order to get there.
Thank you, Matt. So challenges. These are challenges. These aren't roadblocks. These are things that I use as key performance indicators to determine if Cpptf is successful. And really, that boils down to cost certainty for load serving entities and also service customers, and how much cost protection is there for all parties involved. Regulatory, I firmly believe our 30,000 level policy design of a consolidated study has put us in a good position for the Ferc NOPRs that we're currently reviewing. There's indication in those NOPRs to have pre-screening tools, which is part of the CPP process, to better to improve handoffs between the GI and regional planning process. This will help us do that, as putting all the eggs in one basket while we're doing our study. And then it's really making sure we're adaptable to the finer details in those filings and future orders. Another key component of success to us is really keeping the study duration in a manageable manner. Our expectation is to keep it in line with the ITP or quicker. We need to be able to produce timely results on a consistent basis in order to make this an efficient process. And this also provides us the opportunity to do proper scoping in a consistent manner across all of our planning assessments. So those are the challenges, but there also are keys to success with this effort.
And since we're talking about generation interconnection, from a generation interconnection standpoint, what we seek at the end of the day is certainty on cost and schedule. And if we can get there, like Aaron was saying earlier, these projects, if you can have costs and schedule certainty on projects as early on as possible, they become a lot less speculative. And also the shortening of the study allows those projects to move through much quicker. So that, we want to move as quickly as possible to where we're putting steel in ground. Get the study out of the way. Let me put steel in ground, and I can manage that process a lot better, and I can understand that process a lot better. So that's so we appreciate the time. Debbie, we'll turn it over to you, and I think we'll have a question session after the next few presenters.
Thank you so much, Matt and Sunny. That's a really exciting development in SPP, and thanks for sharing that with us. We're next going to turn over to talk about JTIQ. You already heard it mentioned several times in the last few hours. Andy Whitmire, who is the Director of Resource Utilization at MISO, is going to introduce the JTIQ study to us. Andy?
Good afternoon. Sound check. Can everybody hear me all right?
Yes, we can hear you fine.
Great. Yeah, so I'll go over a highlight of the JTIQ, as we call it, or the Joint Target Interconnection Queue Study that MISO and SPP started about almost 2 years ago. It originated from a conversation between our CEOs and the need for us to try and figure out our queue problems together. How do we get more transmission built? We're having our individual queue cycles, we're having large dropout rates because of the high cost of transmission. And is that something that we can try and fix together? And So we started this study process in the hopes of being able to do it within a year. We're able to get the process done in about about 15 months, and then we published the report 1st of March earlier this year. And then since then, we've been trying to work on cost allocation and how we could get this portfolio of projects approved. And we've actually, in the last couple months, we've actually changed gears as to how we might continue to do this process in the future. And we see it as a way to actually replace the effective system study process that we currently have within our individual queue cycle. So SPP has to study the impacts of MISO projects on their queue, and we say the impacts of their projects on our queue, on our system. And so that effective system process can cause a lot of delays and can be expensive. So we think this JTIQ process could be a way to improve that moving forward, and we'll highlight that towards the end of the presentation. And we'll kind of go over the 7 projects that we identified that are needed. And so why are we doing this? Again, MISO SPP, we're experiencing similar resource shifts to a more renewable fleet. And a lot of that renewable generation wants to site in our Western footprints, MISO's Western footprint and the SPP footprint. And the individual costs for projects are expensive and causing a lot of dropouts. So how can we do this together? So when we set out, this was the our scope for what we wanted to do. We wanted to look at 2 things. We wanted to look at, 1, identify what is the best transmission to build in order to facilitate this generation interconnection, and they want to be able to help improve our process alignment through queue priority methodology. And honestly, queue priority was one of the biggest things for us, was to be able to move from a first come, first serve to a first ready, first serve. We talked a lot about in the earlier session about what is the drivers of delays. In MISO, one of the biggest drivers for us is the delay in receiving effects and results from our neighbors, and the fact that their neighbors' queue priorities, that their projects have a higher queue priority than us. Although we want to be able to move faster, we can't because of the way that queue priority was originally set up. It was set up as first come, first serve. So MISO has plans in our projects in our queue that are we're processing our 2020 queue, SCPs from 2017. We need to be able to have a way to allow our projects that are further along to actually be studied first, so that that they get out of the way of lower queue projects. So that was a big improvement for us that we got a FERC approval on in June, and that we hope to we'll highlight that in our NOPR comments to FERC, and something that we hope to pursue with other RTOs to our neighbors. So we started off with our own individual models. The idea to create a joint model and to be able to do it within a year of the original study scope was going to be too difficult. So we started with our own individual models. We used the same type of futures-based assumptions as when we expected future resources to come offline through deactivations and retirements. And then we use our futures that we have both developed individually based on what we think our future resources will cite and where and what type of future resources we expect to see in our futures. Here was the study scope or the timeline of the project. We started again in September of 2020 when we first started. We brought this idea forward, and then we worked through early 2021 on the model development, identifying what transmission constraints we should jointly correct, develop the solutions, do iterative analysis on different transmission solutions, conducted cost-benefit analysis, calibrated all the solutions, and of course, throughout this entire time period, we're having joint conversations and stakeholder meetings with both MISO and SCP stakeholders, and then finalized with the draft report earlier this year, and then the final report was issued at the first weekend of March. And then since then, again, we've been working on the cost allocation and how we can get this project, these portfolios built. You saw this slide earlier in Jonas's presentation. This was the result of the analysis. This 7 projects worth 1.65 billion resolved all of the transmission constraints that we identified as needing to be fixed along our joint seam. Certainly, it increases interregional trans capability, and most importantly, it showed the ability to enable 28.6 gigawatts of combined interconnection service across our footprint. So what we did was we looked at every unit, all the units that we added to our system, and we said if that unit is within a 5% impact of these lines, we'll assume that project is enabling that generation. We ramped it up to see where ramped it up all the way to the top. And then we said if we kept adding more generation there, how much more generation could we add at those spots? And we did that both with SPP and MISO generation. So we estimated it to be able to integrate almost 29 gigawatts of new generation enabled by this portfolio. And now these is mainly fixing the constraints, again, that we identify as part of the study process. It did not address constraints that would be existing next to the point of interconnection of those future resources. So those upgrades would still need to be identified through our individual DPP and DICES processes. And that's the best way to identify the upgrades and assign costs associated with direct interconnection of projects. We also did the economic analysis. Now, this economic analysis didn't assume any of the LRTP portfolio. So in Jonas' presentation, he mentioned how MISO 2 weeks ago, our board unanimously approved $10.3 billion of new transmission within our footprint. We were doing this JTIQ study in parallel with our LRTP efforts. And interestingly enough, 2 of the lines in our JTIQ portfolio were also lines that were identified as needed in our LRTP analysis. Certainly showing why those lines were so important and needed. And so when we did the economic analysis, we did not assume any of that those projects were in the base case because they were not approved yet when we were doing the analysis. So we ended up seeing $724 million of benefit to MISO and $247 million to SPP. Now, we obviously ended up building those 2 projects at top. We built them as part of, or we were going to build them as part of our LRTP Tranche 1. So those 2 lines that are in the green box have been approved by the MISO board, and our transmission owners will end up working over the next few years to site and build those 2 lines. But there are still the remaining 5 upgrades that are still needed. And we've updated the economic analysis since we've gotten the LRTP analysis approved. And with assuming LRTP in the base case, our combined benefits certainly reduced. So we'll have to take that into consideration as we move forward on how these remaining projects get built, because the benefit to load is significantly reduced as far as MISO is concerned for MISO load, because we'll have the LRTP project portfolio being built. That doesn't mean these other lines aren't needed. They're certainly needed to help enable the generation that we expect to come into our queues over the next few years within the MISO and SPP combined footprint. So again, we've pivoted a little bit. We see JTIQ as originally when it was done, we said, well, let's at least figure out what transmission is necessary to at least get the generation that we know is coming, at least get that online. And let's get a portfolio of projects we think we could get built. Since doing this, we realized that, a lot of our problems, Matt just said it in his last presentation, that what TOs want, or what developers want, are cost certainty and timing certainty. And 2 of the problems within our queues is effective system coordination and the time certainty. So we thought, well, if we could give developers that cost certainty, saying, hey, we'll tell you up front what the cost to interconnect within this zone from an effective system perspective, you still would have your costs associated with any upgrades necessary by going through the individual DPP or DICES process, but there wouldn't be any additional costs associated with effective system studies other than this predetermined dollar per megawatt charge that we would assign to future resources coming through our queue to help pay for this set of projects. And so that's how we're seeing a JTIQ being utilized in the future is a replacement for that AFS cost. We would do this study every couple of years. We would more than likely identify different transmission constraints. We would identify different projects that are going to take into consideration multiple cycles. And so doing that longer range planning, taking into consideration more than just the generation that's in a single cycle, you're going to find better, more efficient projects to build. And so we do that every few years, determine what the portfolio cost would be, and then that would then help us determine what that dollar per megawatt charge could be to those projects that come into that effective system zone. And again, we would also look to develop some type of cost between sharing the cost between both future resources and load. So this is our proposed effective system zone. We looked at any node that's within a 5% DFAX from the MISO and SCP scene. And so that's roughly representative of those red lines. And the boxes are the future resources that we had in our study in both the MISO and SPP region. So we would see that if a resource sited within the zone, that those would be the folks who would be charged that dollar per megawatt fee up front. And they would know that when they enter the queue. So they would know up front before the studies are kicked off how much their effective system cost would be. And then again, because we wouldn't be doing an individual effective system study within the queue, then now you're only bound by how fast the RTO themselves can perform their studies and won't have to rely on effective system studies from MISO SPP. You would still have to rely on effective system results from, say, AECI or TVA, as they're certainly impacted by some of the generation that's in this footprint. But will certainly reduce the delayed potential delays that could be caused by that. We also see that the need to split the zone in half. The portfolio that we showed only really addressed constraints in our northern part of MISO footprint, the northern part of SCP footprint. That was because that's where historically we've seen congestion in effective system studies was in those areas. In the south, effective system studies that we've done for each other's queues hasn't seen the need for large upgrades. There's a little bit more transmission capacity in the south. But if we got this process approved, that would be one of the first things we would do is do an effective system study in our southern footprint to identify what are those larger backbone projects that may be needed for generation interconnection perspective to enable future generation in our southern footprint. So again, the benefits of this is it provides cost certainty and timing certainty for MISO generator for interconnection requests to the MISO SCP footprint. It eliminates those unknown effective system upgrade costs. It eliminates the timing delays. It builds on the notion that we've heard from the earlier session and what's been outlined in Ferc's mission NOPR about doing larger interregional type of projects to identify better transmission that's going to enable generation for cheaper costs. So we have really, I think this is a good promising move forward for us. We continue to have stakeholder meetings. Our next one is in a couple weeks on August 22nd. We'll also be looking to now that we seem to have buy-in from most of our stakeholders on this concept, now of course the proof's in the pudding. So what does our new JOA language look like? What are our potential new rates that will be identified? And we're taking those through our individual stakeholder groups, both in MISO and SPP, to get our individual stakeholders particular forums, their feedback on those proposed changes, and hopefully being able to file with FERC by the end of the year. If we're able to file with FERC by the end of the year or early next year, we could potentially have a FERC approval by prior to the summer of next year, and then that would allow these projects to be utilized in 2023 queues when they are kicked off. So that is our hope and in the time that we see for this change. So that's the end of my presentation. I hope sure we'll take some questions in the Q&A later on after the next couple presentations.
Great, thank you so much, Andy. That was a great dive into JTIQ, and JTIQ is just a really nice example of a way that we can start to approach dealing with these seams issues. And I don't know if folks are all aware of some of the difficulties in the timing of the effective system studies and the amount of upgrades that can get triggered as a result of these things. And so JTIQ is a great advancement in the industry. We are now going to talk about a study that we did under an ESIG task force that actually builds on the data that Andy just showed of JTIQ. And this is going to be presented by Bruce Tsuchida, who's a principal at the Brattle Group. So Bruce, I'll turn it over to you next.
Well, thank you. Andrew's presentation was very, very timely because he explained all about what JTIQ was. I don't have to explain it once more because my presentation, given the limited time, is more of a teaser for a webinar that's coming up next week. So I won't go too much into the details, but what we did was we tried to quantify how beneficial JTIQ was. So for this study, what we did was we looked at how much generation interconnection costs, assuming ERISC interconnection, would cost under the status quo, which is the GI studies are done either on an annual or semi-annual basis. And that comes up with a $ per kW number. What happens if the GI studies were performed on 3 years, bundled in 3 years, which is kind of the midpoint between doing GI studies annually today and the 5-year GI study that JTIQ did. And then finally, we looked at what the advantage of JTIQ was. JTIQ did not just look at 5 years, but it also looked at the AFS combination, or it's more of a interregional GI study in my mind. So we looked at these three to compare how the benefits will increase as you go from the status quo, which we call level 1, to an extended 3-year study period. That does not mean that you're waiting for 3 years of projects to sign up. We're just saying what happens if you look at the queue today and bundle all 3 years rather than a single year into one and do the cluster study, to level 3, which we call the high level of proactiveness, or the JTIQ study. A few caveats: that this study is not supposed to be a substitute for any interconnection study. It doesn't consider restudies as part of the process. It does not address cost allocation or participant funding versus crediting for interconnection related upgrades and so on and so forth. It's just purely trying to figure out how much economic benefits would JTIQ bring compared to today, and is there a middle point that other utilities or RTOs can utilize before they get to the golden standard of what we call the JTIQ. So as I said, we looked at 3 different levels. Level 1 is the status quo, where the RTOs and the utilities perform the cluster studying on an annual or semi-annual basis. Level 2, we basically said, what happens if you do it on, if you look ahead for 3 years and combine all the resources, all the projects that are in that 3-year window rather than a single year. And then the last one is the JTIQ. Our assumption is that because renewables are location limited, for example, you can build gas plants anywhere as long as there's gas pipelines and interconnection locations. But renewables are really location dependent. If there's a preferred wind location, even if a specific project withdraws, someone else is going to come in. So the odds of that interconnection study being wasted is very, very low compared to your traditional thermal asset, which the original Ferc Order 2003 interconnection study process was developed on. At the bottom of this page, you kind of see how much project counts we're talking about. Level 1, if you look at 6 months or 12 months, looking at SPP, you got about somewhere between 1,000 to 5,000 megawatts of interconnection projects. Level 2, which we call it 3 years, you're talking about 3 times that. And level 3 in JTIQ, the study I think looked at 40,000 megawatts of interconnection projects and then expanded it afterwards. This slide shows what you probably saw more than 3 times today, so I won't go into it, but the JTIQ basically identified 7 projects at the cost of $1.65 billion, which will allow you to integrate 28.6 gigawatts of new GI projects, assuming an ERIS. And associated with that $1.65 billion, there was almost $1 billion worth of production cost savings that was there. So we'll show the numbers for the 2 cases with the production cost savings accounted for and without it accounted for. We had the JTIQ study, so we looked at what regions should we actually study within the greater MISO and SPP footprint. And for convenience, just so that it aligns with what JTIQ was doing, we looked at Eastern Nebraska to represent the SPP and Eastern Dakotas to represent MISO to calculate the level 1, which is the status quo, and level 2, the medium level, or the 3-year assumption. For level 1, which was looking at the current studies, it was pretty simple. You just look at the current studies, figure out how much the cluster study costs altogether, divide that by the total number of megawatts that were included in projects studied in that, and that becomes your $ per kW cost. For level 2, we actually had to develop a semi interconnection study looking at thermal violations. And for that purpose, we selected 960 megawatts from Eastern Nebraska and 2,300 megawatts from Eastern Dakotas. We created a semi-loop or potential interconnection or transmissions to accommodate those projects, and came up with a number. And for level 3, we looked at the JTIQ study. And as I said earlier, you got the JTIQ study with and without the production cost savings that MISO and SPP identified. So the summary is that by going from a single year study to a 3-year study, you're reducing the cost by give or take 16%. Now going from the 3-year study to the 5-year study, but also enhancing the study scope to include what JTIQ did. Again, I in my mind, that is basically a inter-regional GI study that includes all other transmission upgrades as well. The benefit increases from 16% to almost half, 51%. So by doing the JTIQ, you're effectively reducing the interconnection cost on a $1 per kW cost into half. Now, if you also account for the almost $1 billion of adjusted production cost savings, you're reducing the interconnection cost down to about 20% from what it originally was. Now that requires a methodology of allocating that cost to the generators or whoever paid for it. But in either case, even if you don't account for that almost $1 billion adjusted production cost savings, you're halving the interconnection cost by going through this process of JTIQ, showing how superior it is compared to what we see today. The chart on the left-hand side shows how the benefits are growing. I used the word exponential, but some of the reviewers said, no, it should be non-linear. I haven't made up my mind which word to use, but that chart kind of shows where we are. If you do it on an annual basis, the cost is a little bit shy of $120 per kW. In certain years, we saw sometimes the costs go up to $400 or $500 per kW a year, especially on years where you have limited interconnection in the cluster study. If you do it on a 3-year basis, it goes to about $95, but the JTIQ brings it down to less than 60 or to about 25 if you include the APC benefits. A few qualitative assessments associated with it is that obviously the proactive GI planning, including inter-regional studies, can help bridge the gap between the short-term GI studies that typically look at the least cost and done within 5 years to the long-term transmission planning studies that are typically looking at the highest net benefit, not necessarily the least cost, and looking at 10, maybe 20 years. But it helps bridge that gap while providing a significant amount of benefits for the GIs. The other thing is the cost allocation mechanisms is obviously a concern, but there are other examples where the latecomers have to pay their share for the earlier investors. Ferc has approved tariff provisions for New York ISO and MISO of that nature. And also, if you look at proactive transmission projects like the MISO MVP, the SPP priority projects that build the double circuit 345 kV and the collector systems, or California Tehachapi, ERCOT CREZ, which is not under FERC jurisdiction, they are all fully subscribed. So perhaps the concern that you may not have enough off-takers is moot at that point. But all in all, what we found is that if you expand the study scope and the period that you're looking into for developing the interconnection solutions, it has a huge benefit. Even if you just expand it from the current 1 year to 3 year, you're reducing the interconnection cost by 15 to 20%. So that should be material. And if the whole world looks at JTIQ and finds it useful and they follow path, then you have the potential of reducing interconnection costs down to half, or even more, down to a quarter of what we see today. The last slide talks about the study limitations. I kind of briefed that over at the very beginning, so I won't bore with you with that. But and here's the table of contents of the total report that we're finalizing right now. If you are interested, please listen to the webinar that's coming on in 10 days or so, maybe a week or so. So with that, I'll hand the mic back to Debbie.
Great, thank you so much, Bruce. It's a really exciting study showing that being more proactive in generator interconnection saves you money. And it's some nice information that'll be presented in a week's time. So now we're going to switch gears just a little bit, go back to something that Hannes mentioned at the very beginning about the needs to link generator interconnection with transmission planning, and to think about transmission planning in a multi-value benefit perspective. Derek Stenslick, who is the founding partner of Telos Energy, recently completed a task force with us at ESIG quantifying the multi-value benefits of transmission. And he's going to show some of those examples and analysis in this next presentation. Derek?
Great, thank you, Debbie. And as Debbie said, we recently at ESIG finished up a task force looking at multi-value benefits of transmission planning, and specifically looked at a case study in ERCOT and as well as an inter-regional case study to really try to quantify some of the benefits and establish a methodology to bring in benefits beyond just production cost savings, which is kind of the de facto metric for regional transmission planning. What I'll try to do today is kind of leverage that to talk a little bit, make it applicable to generation interconnection, but really talk about transmission planning more broadly and more holistically. So for more details, similar to Bruce's last presentation, this is a report that we just published maybe 2 months ago. You may have seen the webinar we released with that as well. If you haven't, there's links to both of those. You can go on. If you just Google ESIG multi-value transmission planning, you will go right there. So we started the project with talking to several transmission planning experts across the industry, people from utilities, grid operators, developers, other consultants, several of the folks that have been presenting today. And from that, we really solidified 4 barriers that we thought were most pressing for transmission planning, specifically around integrating renewables and getting to that clean energy future. The first is on focus. There's a focus on local reliability rather than regional economic efficiency. Hannes covered that really well. Second, which most people are talking about today, is around interconnection queues favoring short-term network upgrades rather than proactive planning. So really kind of in line with what Bruce just presented on. Make sure I'm muted here. The third is around lack of interregional planning and kind of what you've heard recently with the JTIQ as being an example of how to overcome that, and then cost allocation. So all the things that we've been talking a lot about, we tried to solidify and really explain in a concise manner as really some of the 4 barriers. I think what we'll talk most about today is the top 2. I'll go over this really quickly because I think this has been iterated over and over again by a lot of the speakers. Definitely worth mentioning because if it's come up now with 4 or 5 different speakers today, chances are it's an important topic. So really, what I wanted to illustrate here is today there's kind of 2 silos, and I think Hannes' slide divided this up further into maybe 6 or 7, but there's a couple silos in transmission planning. There's the generator interconnection, and then there's regional transmission planning, or like the really large scale system studies. The generator interconnection is really local reliability focused, although we see reliability issues pop up, hundreds of miles away, whereas regional transmission planning is kind of full system-wide analysis, looking at multiple years, generator interconnection, looking at kind of some of these snapshots. And what we see is there's very limited overlap and coordination between these 2 silos today. There's obviously a couple places like the JTIQ where we're seeing some of these silos break down, which is a good thing. But really wanted to illustrate that today, still 2 separate silos, and we see a lot of inefficiencies. So where could this go? Where do we need to go? Is really start to merge and get to that sweet spot in between the 2, where there's integrated generator interconnection and regional transmission. And to do this, really think about multi-value benefit planning. So not only can large-scale interregional transmission help on the economics of the system, help on the reliability of the system, it can also help integrate renewables. And that's really integrate any new generation, which obviously if you look at the interconnection queues today, most of that being renewables. I think a lot of folks have talked about that today. So what I'll do is focus on this multi-value and multi-benefit approach that we evaluated in the ESIG task force. So again, we looked at how can we implement this multi-value framework to look at transmission upgrades. We wanted to do this as a way to influence the Ferc NOPR or to provide some analysis to support comments on the Ferc NOPR on regional transmission planning, and really develop a playbook that we thought, while some places are doing a lot of this in some of their analysis, develop a playbook that transmission planners across the country could pick up and say, let's test out X, Y, Z in our planning and do it in a consistent manner. So we identified 6 benefits: production cost savings, the de facto benefit for most regional transmission planning or economic transmission planning today. And obviously that remains important. But what we see is as wind and solar, which are zero marginal cost resources, increase on the system, that drives down our production costs. So as a result, it's also going to drive down production cost savings over time, attributed to new renewables, or it's to new transmission. And that's going to happen at the same time we actually need more on the system. So if we just look at production cost savings or adjusted production cost savings, taking into account imports and exports, we're missing a lot of value. And that was really the premise of this white paper and of this study. Second was around what we identified as capital cost savings, and really here, the ability to go after lower cost generating resources, and generator interconnection is a piece of this benefit. The third is around emissions benefits, both kind of emissions benefits that can be quantified or monetized today with different markets, but also ones that there's a public benefit that doesn't always get quantified. I think the value that we tried to bring, and what I would say is unique about the work we did, was the bottom 3. I call them the 3 Rs: risk mitigation, resource adequacy, and resilience. So what we meant by risk mitigation is transmission planning tends to look at a a very narrow view of what the future could look like. It doesn't look out far enough oftentimes. It also doesn't look at a wide enough range of potential futures. We don't, transmission planners, power system planners, we don't have a crystal ball. There's a lot of uncertainty. I think we're living through some of that uncertainty and volatility right now. And it's really taught us to widen the lens that we look at. So that's true for economic transmission planning. It's even more true for generator interconnection planning, which not only looks at a very narrow slice of future conditions, but it's even looking at a few snapshots of those future conditions, maybe just 2 or 3 hours, and basing huge network upgrades based on a very small window of potential future conditions. And so we looked at a way that transmission can be used as risk mitigation for that uncertainty. The fifth was around resource adequacy and really framing transmission as a capacity resource. So the same way we do evaluate load carrying capability of different generation, you can do the same thing for transmission, and we showed that especially in an interregional transmission planning. And then lastly, on resilience. So not only does it kind of provide kind of firm capacity or capacity credit for our conventional loss of load expectation and capacity needs, but also in extreme events. And that's very basically lessening the severity of events when they do occur. So those are the 6 main benefits. We went through in the report, we looked at 2 case studies, one looking at the West Texas export, which a lot of people in the generation interconnection queue are obviously well aware of. It's a large transmission constraint that's going across from West Texas to East Texas in the load center. Now, in the short term, being one of the largest constraints to new renewable development in Texas. We looked at that case study. The second case study we looked at was an interregional transmission line from Southern Company into ERCOT to understand what the benefits of that. So I wanted to focus certainly on the need to look at not only production cost savings, but reduced capital cost benefits. And here I have a map of very generic levelized cost of electricity for both wind and solar resources in Texas on a county by county basis. What you can see is it's no surprise we now have a constraint on the export of wind and solar resources from West Texas to East Texas. West Texas is one of the best renewable regions in the country, both in terms of the actual renewable wind and solar resource, as well as the ability to site new resources and develop projects. And so what you see, that threshold of that white line of where the West Texas export is, no surprise, a very good renewable resource zone to the west of that, the load all sitting to the east. And really, if you look at transmission benefits today, and most of the time where you look at production cost savings, which up until recently was the only metric used in ERCOT to justify new economic transmission builds, it doesn't take into account the lower cost of accessing those renewables, both in terms of the LCOE, but also on the generator interconnection. So if you build out transmission, not only do you access lower cost renewables, you also enable that renewable capacity better from lower interconnection costs. So that's what we tried to quantify here and just looked at that differential between LCOE between East and West Texas and added that additional benefit to the transmission. And again, no surprise, I overlaid on this the original CREZ build out of the 345 kV network to access those renewables. Very successful, I think, a good example of how you can build out the transmission before the generation's even there, before the queue is fully there, and then it will build it and they will come. Kind of lowers the generation interconnection hurdle as well as provide significant economic benefits. So I alluded to this before, from looking at a wide range of future conditions. And so for this, I think Hannes talks about this as a scenario analysis. We looked at both scenario analysis and stochastic analysis on top of that. So we looked at 3 different scenarios of different renewables and retirement levels in Texas, across 40 stochastic samples of gas and load. And again, really just to identify the methodology of coming up with 120 different future conditions that we evaluated that on. And what you see in this is that under normal conditions, the transmission is beneficial, but maybe not, a huge benefit to cost ratio. But if you start looking at some of the tail end of that distribution, there are scenarios where transmission has huge upside, and there's very few scenarios where it actually leads to a net cost. So something that I think we don't do a great job at in the industry across the board is looking across the distribution and understanding probabilities of different outcomes. So this is an example coming out of the West Texas analysis where we build up this waterfall of the different benefit categories until you get to a total benefit here relative to the total portfolio investment. You can see net benefits greatly exceed the net cost or the total cost. And if you just looked at production cost savings alone, it would be about break even, probably wouldn't be enough to justify new transmission. But if you really look at the stacking, you see a huge flip to the benefit cost ratio. You'll notice here that resource adequacy and resilience, we assign no value there. And basically the reason for that is there's already a huge amount of renewables in West Texas. So adding even more doesn't really differentiate the portfolio mix, doesn't add significant resource adequacy or resilience benefits, although there are probably cases where you could make certainly justify some benefits there as well. So we try to be conservative in that outlet and instead looked at an interregional transmission link to quantify those resource adequacy benefits. So again, accessing low-cost renewables or decreasing capital costs of new resources, also very applicable to interregional transmission, especially if you have a region that is now able to access lower cost renewables, especially diverse renewables in wind resources in Texas. So we quantified that. But importantly, also quantified the resource adequacy benefits. And this was probably one of the biggest outcomes of the study, was looking at resource adequacy of the two isolated systems. So ERCOT on its own, Southern Company on its own. We intentionally brought both of those systems to a loss of load expectation of over 0.3 days per year. So intentionally, again, started that at an unreliable point in 2030 just by making retirements. Not to say that it will be unreliable in 2030, but wanted to start at a place where most people would say that there's insufficient capacity, but without adding any new generation resources, we're actually able to bring the resource adequacy of the system on both sides of the transmission line down to an acceptable threshold. And that was a really key contribution. A 2 gigawatt line would have the capacity credit essentially of 4 gigawatts because it provided full benefit on both sides of the line without adding any new generating resources. The really key benefit as we start to think about maybe proactive transmission planning for generation interconnection, we also have to look at what are the other values that are out there. Are there resource adequacy or capacity benefits that we can also bring? Again, I think a few people made the point, cost allocation is really tricky. It gets a lot easier if we can show there's a wider array of benefits that everybody can benefit from. And again, this is the value stack for the interregional transmission, where you'll see a kind of an inverse of what we looked at in the West Texas transmission upgrades, where here there's more significant benefits on resource adequacy and resilience. And the big takeaway here is different transmission will bring different benefits. And I think that's something we really wanted to highlight, is the need to really look across a wide range, and generation interconnection is no different. So we want to look at that here as well. And that is all I had. Just wanted to give special thanks to my colleague Ryan Dio, who also helped on the project, as well as all the other members of the ESIG task force. So Debbie, back to you.
Great, thank you so much, Derek. And I'd like to ask now all the speakers to maybe turn on your video, and we have some questions lined up in Slido. And I'm going to try and stick to the questions that are sort of most directly relevant, and there's some clarification questions in here. So I think first for Matt and Sunny, there's a question about the CPP process and how different service types like ERIS, NRIS, TSR can be studied in a consolidated way to accommodate the different services requested.
Sonny, you want to start? Or
Yeah, sure thing. So we're at the beginning phase of designing that CPP process, but one way that we've discussed on implementing that is through scenario modeling, rethinking what are we trying to model with a capacity model versus an energy model. Capacity being firm service scoped, and then energy being non-firm. So there may be some market-based flows in that, and then could also potentially be paired with your ERAS service, your as available service. So just had some preliminary thoughts on that topic in the group. We're definitely going to talk about that a little more as we get into the design phase. I'll see if Matt's got anything else he'd like to add to that.
So I think that those are the considerations going into CPP. On a shorter term basis, there's also a consideration of a capacity resource product in SPP right now. Currently that doesn't exist. So a lot of the interconnections are tied to the transmission service. And because SPP doesn't have a formal capacity market, the Nrs product is not very valuable for generators. So there's really no reason to use it at this current time. But the capacity resource product will change that in the future. So I think that's also going to be incorporated into CPP. So a little bit of a compound answer on various models that will be incorporated.
Sure, thanks. And Andy, let's see, regarding your slide 9, and I don't know, it might be too difficult to bring that up right now, but could you clarify whether the $1 per megawatt charge that you suggested would include additional system upgrade charges or not?
It would. So that $1 per megawatt charge would only account for the effective system charges. So if you're a project in the MISO queue, that's the set known charge that you would be assessed for effective system charges within SPP. Similarly, for SPP, those would be the charges that you would be assessed to account for a MISO effective system. You would still be assigned whatever the upgrade cost would be through the DPP or DICES process to determine what the actual upgrade costs necessary for the point of interconnection for which you chose.
Great, thanks, Andy. So there's some questions sort of around, the scope of what we discussed today. So we discussed a lot about MISO, we discussed a lot about SPP. So folks are also interested in other regions. And then also, of course, in the West, where we don't have RTOs except for Cal ISO. I'm wondering if anyone wants to comment on either some of those other regions or what we might do for reform in the West. Is anyone interested in taking that on?
Well, Debbie, when we started the GI study, timingly when the JTIQ came out, before we decided to choose SPP and MISO because of JTIQ, we were also thinking about doing a vertically integrated utility, including the cost allocation at some point as a potential phase 2 of the study. We could actually do something like that, pick up a vertically integrated utility in the West to figure out what the benefits of proactive transmission planning combined with GI could do. But that's just a thought.
Sure, thanks. Anyone else? All right, maybe I'll move to the next question. So one person is worried about, because we focused here on speed and efficiency of generator interconnection, are we sacrificing reliability as a result of these streamlined and faster processes? So I wonder if anyone has any thoughts about that interplay and what you're doing to ensure that we're still ensuring reliability of the system.
Yeah.
Go ahead, Andy. No, I was just going to say, I think from a generator perspective, I think reliability is in the mix of that certainty that we want both on cost and schedule. If we don't have a reliable system to interconnect to, you're going to be subject to significant curtailments. You're potentially not going to be able to interconnect. And I think those are the issues that we see from our side. When we say, certainty on cost and schedule, I think that reliability is a large component of that. But at the same time, those reliability issues are not going to be sacrificed for the speed of the study. In fact, if you get the automation right in our CPP process, in my view, you're going to be incorporating a lot more of real-time reliability impacts because you have better data and more of that data coming in. So that's just my 2 cents from a generator perspective. Andy, I interrupted you.
No, I mean, it's what MISO did through LRTP, what MISO CP are doing through JTIQ, this higher level identifying what upgrades are needed before the projects come into the queue and anticipation for what will come in. It is important, right? I mean, that's MISO's committed to continuing doing LRTP. We want to make JTIQ a repeatable process with SPP. If that's successful, we want to continue that with our other neighbors, like potentially try and do that with PJM. But from a reliability perspective, you still would have to do your individual queue cycles, right? You still have to identify what are the reliability issues identified with that exact point of interconnection. So although it's important to continue to look from a broader perspective and build transmission, build it so they will come, once you find out where they actually want to connect, because there's a lot to it than just mission cost, right? There's local siting and permitting and everything else. So that certainly plays a big part into where you can actually develop generation. So when you find that spot and you come to the queue with your site control, we want to be able to give you what is necessary for you to reliably connect to the grid as fast as possible, right? So that's the whole point of a cluster study. That's the whole point of all the enhancements that MISO has done over the years, is to streamline that process. But the whole basis of it is still going to be reliability based to ensure that you're identifying what are the main reliability issues that exist for that point of interconnection that you picked.
Great, thanks, Andy.
And one other comment about the reliability versus speed. I don't even want to call it a trade-off, but the concern that there's a trade-off, I think is, and Matt brought this up, if you look at the ERCOT example, it's the ability to interconnect or have the facilities to interconnect. The resource can always be curtailed. Now that's obviously not a good outcome, but maintaining reliability, you can treat it as if the generator is not there. So that's another tool to somewhat mitigate that concern.
Yeah, Debbie, I just want to add that I think under the CPP structure, there's the opportunity to improve reliability. It's not necessarily just a trade-off with speed, but you get to consider other components, other scopes within one study that should help us have more reliable answers, more optimal answers in the actual system needs. So I think the CPP concept does give us alignment and improved reliability outlook.
Excellent, thanks, Sonny. Bruce, there's a clarification question for you, asking about the timelines to complete proactive planning studies and how that impacts interconnection process timelines.
So all we did was we did not adjust or discuss any of the timelines associated with the interconnection process per se. What we simply said was today the interconnection studies or the cluster studies look at 1 year worth of projects. What happens if you look at 3 years worth of projects rather than a single year? And what happens if you look at 5 years worth of projects combined with the AFS? So we did not discuss or study how long the whole process takes. We did not look into whether there's going to be computational savings or whatnot. It was just saying what happens if you expand the scope of the current GI study. That's all.
Okay, great. Thanks, Bruce. I realize we're getting towards the top of the hour and Julia needs to close out. So at this point, I would like to thank all of our speakers. Again, huge round of applause for you guys to share with us what you've been doing in your different RTOs and through your different analyses and the great work that's been done to try and further solutions in this space. So with that, thank you all again. And I'm going to turn it over to Julia.
Yeah, thank you all for the great day, great presentations. We'll start again tomorrow at 1 p.m. Eastern time, and we'll focus on interconnection studies and modeling piece. And I also would like to add that we'll try to address all unanswered questions, and we'll post it together with the presentations on the event page. So there'll be a spreadsheet with Q&A there, so look for it. Thank you, and see you tomorrow.